Hi everyone, so in this video we are going to learn about static timing analysis, a very important topic for digital design placements and sometimes it is confusing as well, so that we will learn and in a very good manner we are going to learn it. But before starting the video, if you are looking for a complete course where we are covering everything that is required for digital design placements, so you can go to our website prepfusion.in. You need to type prepfusion.in or I will put the link in the description as well, and you can purchase these courses. This is for digital design and this is for analog VLSI design. Okay, so if you are interested in the courses, then you can purchase it. Now after this video, this would be of roughly around 3.5 hour video or 4 hour video. After this video, what I would be expecting from your side? Comments. Okay, only what I am expecting, comments. If you found the video helpful, if you have any other suggestion, whatever that you want to write, I would expect that you would be writing something, and that would keep me motivated to bring more and more content on YouTube. So after the video, you can comment down your reviews or anything that you want to deliver or anything you want to write down, that you can write down. Okay, so now let's start learning our chapter, that is static timing analysis. Hi everyone, so in this video we are going to start studying about static timing analysis. Okay, very interesting topic and a very easy topic. No need to be worried about this particular chapter or this particular topic. A lot of students are oftenly confused in this topic, but we will see in a very good manner, in a very in-depth manner, and once you are done watching this video, after that you will be very comfortable with this particular chapter. Okay, so what we will see some important terms, because these terms will be used again and again, and in some interviews they can ask you the meaning of these terms as well. Okay, in some easy interviews they will ask you what is the meaning of contamination delay and propagation delay. So what is the meaning of that? So better writing down the definition, we will understand it by an example. So this is an inverter, input is A, this is the output, this is the output of inverter, and applied input is A. Okay, contamination delay is given as 2 nanosecond and propagation delay is given as 3 nanosecond. Now what they are saying, at t equals to 0, your input is changing from 1 to 0. You need to draw the waveform at B. Contamination delay is 2 nanosecond and propagation delay is 3 nanosecond. Let's see what does it mean. So for t less than 0, input was at 1, right? Because they are saying that it is changing from 1 to 0. For t less than 0, it was at 1. So certainly your output would have been at 0, because this is simple inverter. Now what they are saying, now it is changed to 0. So where will your output go? B will go to 1, that I know. B will go to 1 now. From 0 to 1 it will go. But there is contamination delay of 2 nanosecond and propagation delay of 3 nanosecond. So what will happen is that B will start trying to go to 1 at 2 nanosecond. It will start trying to go to 1 at 2 nanosecond. So it will start trying to go to 1, and at 3 nanosecond it will reach 1. Did you understand this point? So this was your contamination delay and this is your propagation delay. That means you have reached till the final state. This is the steady state, right? This is the steady state. Steady state is 1. So propagation delay is the time required to reach the steady state, and contamination delay means it will start going towards the steady state. Why is that happening? That is of no use actually, but let me just tell you. Let's just say you design this inverter. So this will have some output resistance. Also there will be some parasitic capacitance as well. So it will frame a RC circuit. Basically, if you are applying, this is simple inverter, right? This is inverter. It is having some output resistance and some parasitic cap will also be there. So it will not instantaneously charging, right? It will charge exponentially. Slowly it will be charging. So from 0 to 1, if it is going, it will take some time. If you apply 0 input here, this will become 1. Now this is your final output. So to go to the final output, that means to be 1 here, it will take some time. Okay, so just as it starts charging, that time is known as contamination delay, and when it reaches the steady state, that time is known as propagation delay. Okay, so this is your propagation delay. So that is the point. I hope you must have understood the meaning. Contamination delay is the time when it starts going towards the steady state, and propagation delay is the time when it has reached till the steady state. Very easy concept, very straightforward. Sometimes people get confused what is contamination delay and propagation delay. Now you are good. Now you are good with that, right? Now let's understand the most important term. The whole chapter will revolve around this, that is setup time and hold time. What do you mean by setup time and hold time? Okay, so before writing down the definition, first we will understand the meaning of that. So this is a D flip-flop. Clock is applied, positive as triggered clock is applied. This is your data input. what is given? Setup time is 3 nanosecond and hold time is 2 nanosecond. This is your data. This is your input data. This is t is equal to 0 nanosecond. This is t equal to 8 nanosecond, and clock is applied in this manner. In this manner, clock is applied. So this is your positive edge is coming at 4 nanosecond. So just as the positive edge comes, this is a positive edge triggered flip flop, right? Positive edge triggered flip flop it is. So just as the positive edge come, what is the job of this flip flop? That it will just retain this data, right? It will just capture this data. What is the job of D flip flop here? What is your Q plus? Q plus is simply equals to data only. So how will your output look like? If you don't know what is setup time, if you don't know what is hold time, then how would you make your output? Output means I am making my Q. So how would you make your output? That you will start that, sir, initially it is 0. Just as the positive edge comes, it will see what is applied here. 1 is applied. So it will sample 1. Now it will sample 1 until the next positive edge, it will sample only 1 only. Then it will again see what is applied. Okay, 1 is applied. So till the next positive edge, it will sample 1 only. So till now, this is what we have seen. But now what clock will say? Now what clock will say? Clock will say that yes, I will sample this data. I am supposed to sample this data. That yes, I will sample this data, but I will look back and look ahead. I will look back and look ahead. What I will look back? That this data, whatever the data we are having, what data we are having? Data 1 we are having. So this data should be stable for the given setup time. So if my this flope is having 3 nanosecond setup time, that means I will sample this data only when this is constant for previous 3 nanosecond. Also, it should be constant for next 2 nanosecond. So this is your T setup and this is your T hold. So just as the positive edge comes, this positive edge will tell that what is your setup time? Your setup time is 3 nanosecond. So yes, whatever the data I am having at positive edge, that should be stable for the previous 3 nanosecond as well. And also, what is your hold time? Hold time is 2 nanosecond. Also for the next 2 nanosecond as well. From here to here. This is my setup margin. And this is my hold margin. So this is what your clock will say. Okay. So here, yes, it is stable because this is 0 nanosecond. This time is 4 nanosecond. So 4 minus 3, this time would be 1 nanosecond, right? And 4 plus 2, this time would be 6 nanosecond. So it is lying in this boundary only. So the data is stable here. The data is stable. In this window, data is stable. Say yes or no? Because this is 0, this is 1 nanosecond, this is 6, this is 8 nanosecond. So in this window, data is stable. That means there is no setup violation. Violation means like condition is satisfied. No setup violation and no hold violation. Did you understand the meaning? Are you understanding the meaning? That data should be stable just as the clock trigger arrives. The data should be stable before some particular time. That is known as setup time, and it should be stable after the clock age for a certain time. And that time is known as hold time. Okay. We will write down the definition, but let's see more examples. It will be more clear to you. Now your setup time is 5 nanosecond. Okay. And hold time is 2 nanosecond. Just as the positive edge arrives, what it will see? Here it will see that 1 should be sampled. But I will sample 1 only if it is stable for previous 5 nanosecond. Because setup time is 5 nanosecond. So it should be stable for previous 5 nanosecond. This time is 4 nanosecond. Right? This time is 4 nanosecond. Where will 5 nanosecond come? 5 nanosecond. Previous 5 nanosecond. So this is 0 nanosecond. Basically this window is 4 nanosecond only. This window is 4 nanosecond. So 1 more nanosecond will be somewhere here. So it will look back for 5 nanosecond. What is there? Here data is changing. Are you getting this point? This much is your setup time. This much is your setup time. So now when the positive edge looked back, what did it see? That no, I am not having data 1 here. I am having data 0 here. So I am not going to sample it. So there is setup violation. Okay. And what about hold violation? Is there hold violation? No, hold violation is not there. But because what clock edge will do? It will look for further 2 seconds ahead, 2 seconds ahead. So what it will see? 2 seconds ahead means 4 plus 2, 6 nanosecond. So till 6 nanosecond, what it will see? This is the hold time. So till 6 nanosecond, yes, data is constant. So hold violation is not there. No hold violation. Setup violation is there. No hold violation. So if setup violation or hold violation is there, then your output will be undefined. Okay, it will go into metastable state. So let's not take these names. Just you need to know that if violation is there, your output will be undefined. So you cannot draw the output here. You cannot tell whether 1 will be sampled or 0 will be sampled. Okay, so output is undefined. That you can say that my output is undefined. Okay, so you don't know whether output will be 0. Like this one will not be perfectly sampled. It was supposed to sample this one, but this one will not be perfectly sampled because there is a setup violation. So in your digital circuit, you need to avoid these violation. How will you avoid it? That we will study. But first we are looking at the concept. Like what do you mean by setup time, hold time, why there is a violation? So that we are looking at. Now see, solve this example on your own and tell me which kind of violation will be there. Setup violation or hold violation? Setup hold violation. Why is that so? Because this clock which is arriving at 4 nanosecond, it will look back for 3 nanosecond. Looking back for 3 nanosecond. That means where it will reach? It will reach at 1 nanosecond only. At 1 nanosecond, it is constant only. It is always constant. It is always constant, right? And it will look ahead for 3. It will look ahead for 5 nanosecond. So 4 plus 5, what that would be? 4 plus 5. That would be 4 plus 5 nanosecond. 4 plus 5 nanosecond, that would be 9 nanosecond. So at 9 nanosecond, you are having 0. Here you are having 1 and here you are having 0. So not satisfied. So there is hold violation. Okay. And no setup violation. Right. Let's see this example. Now, why I have made the data line like this? Do you remember the first lecture, the very first lecture of digital electronics? What did I tell you there? The data is actually shown by this. What do you understand by this particular lobe or loop, whatever I can call it? What do you understand by this? That I don't know whether my data is 0 or 1, but I am pretty sure that in this much of window, my data is constant. Okay, so in some textbook or not in some textbook, in 100% of the textbook, data will be shown like this only. That I don't know whether it will be 1 or 0, but I am pretty sure that in this window, my data is constant. Whether it is 1 or 0, but it is constant. In this window, I don't know whether it is 1 or 0, but it is constant because data can be random 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 1, anything it could be. But clock will be always 0, 1, 0, 1, 0, 1. So clock will never be shown like this. If something is shown like this, that means certainly that is representing data. So that we have seen in the first lecture only. We saw about data rate, so all kind of things we have seen, right? So now I know that in this window from 0 to 8 nanosecond, my data is constant. So at 4 nanosecond, the clock as is arriving. At 4 nanosecond, the clock as is arriving. So what it will do? It will look back for 5 nanosecond. It is looking back for 5 nanosecond. Looking back for 5 nanosecond. Okay. So where it will go? It will go at this minus 1 nanosecond, you can say. This will be minus 1 nanosecond. In the first example, what did I write? When it was looking back. Yeah, so basically this is minus 1 nanosecond only. The same concept is here. So if it is looking back for 5 nanosecond, that means at minus 1 nanosecond it is looking. I don't know whether it is 0 or 1, but certainly here it is constant. But now we are going into the other lobe. We are going into this lobe. So we are not sure about this data whether it is 0 or 1. It could be 0 as well, it could be 1 as well. Let's just say if it was 1 and what if it was 0? So yes, there is setup violation. And here as well, it will look for next 5 nanosecond. So that means it will fall somewhere here. So again, we are not sure whether it will be 0 or 1. Let's just say if this was 1 and this could be 0. So again, there is hold violation as well. But what if the hold time was 2 nanosecond only? If hold time was 2 nanosecond only, then we would be falling here only, right? If hold time was 2 nanosecond only, then we would have fallen in this lobe only. Then I would know that if this is 1, then certainly this is also 1. So then I would say that there is no hold violation. But now, in this case, what is the scene? This is the scene that I don't know whether it is 1 or 0, but it is falling into other lobe. That means certainly there is setup and hold violation. Setup and hold violation. Okay. So this was the meaning of setter time and hold time. You can read the definition. The amount of time for which the input must be stable before clock transition. So before clock transition, input must be stable. For this much of window, input must have been stable. Here you can see before the clock transition, for 3 nanosecond, your input must be stable. Okay. And after the clock transition, amount of time for which input must be stable after clock transition. So after clock transition, it should be stable for this much of window. After clock transition, it should be stable for 2 nanosecond. So yes, it is stable for 2 nanosecond. So this is known as hold time. Okay. So I hope you must have understood the meaning. What is the meaning of setter time and hold time? On top level, whenever the clock edge arrives, it will look back and look ahead. When it look back, it will see that my input should be stable for the given setup time. And when it is looking ahead, it will see that my input should be stable for the given hold time. Okay. So look back and look ahead. If you are looking back, that means you are looking at setup time. If you are looking ahead, that means you are looking at hold time. I hope this is crystal clear to you. Okay. Let's move ahead now. What is clock skew? Okay, so this term will be again and again used. No one will ask you in the interview that what do you mean by clock skew. Hopefully no one will ask you, but this term will be again and again used. So when you design a chip, no, I will tell you the practical meaning. So when I am designing a chip, there will be a lot of blocks. There will be a lot of blocks, but there will be one common clock. Okay, so let's just say these two blocks are there. I will be feeding this clock to this block as well and to this block as well. Now they will be far away from each other. No? On a chip, one block will be here, one block will be here. So they will be far away, right? Now this clock is given to this block by this particular wire, and this clock is given to this block by this particular wire. This particular clock is given to this block by this particular wire, and to this block by this particular wire. Now all these wire will have their some parasitic. Parasitic means there will be some resistance, there will be some capacitance. If there is some resistance and capacitance, that means it might happen that this wire has lower capacitance. If this wire is having lower capacitance, that means, sorry, this wire can have higher capacitance. Higher capacitance means time, what do we say? Time constant is high, right? Higher capacitance, tau is equals to RC. If that means time constant is high. If time constant is high, that means it will take more time to reach here. And if this is having lesser time, if this is having lesser capacitance, that means it will take less time to reach here. So basically there will be different wires. The length of wires could be different, and based on the length, the capacitance could be different. And based on the capacitance, it may take more time or less time to reach to a particular block. So let's just say the clock is reaching here at t equals to t1 time, and clock is reaching here at t equals to t2 time. And I am assuming that t2 is greater than t1. Assuming that these are two different blocks. It could be D flip-flop, it could be any register, it could be anything. These are the blocks on your chip. The clock is reaching here at T1 time, the clock is reaching here at T2 time. What I am assuming? I am assuming that T2 is greater than T1. So what will be my clock skew? T skew I am writing. So T skew will simply be T2 minus T1. Okay. So whatever the time difference is there, that is known as clock skew. Okay. So that will depend on parasitics that you will learn when you go to the industry. So when you design a chip, these kind of things will come in action, that you need to decrease the wire length when you design on chip. So these kind of things you need to do, and based on that only you need to make your design. So these terms will be again and again used in your industry, that clock skew. Then there will be a term called clock jitter. Okay. So here the clock are reaching at the same time only. Both are reaching at the same time. T equals to 0 nanosecond I am calling it. But what happened is that this was your ideal clock, but when it reached there, the time period got changed. Here it is fine. Here it is fine. But here what do you see? The time period got changed. It was supposed to give negative edge trigger here, but it is giving negative edge trigger after some time. It was supposed to give positive edge trigger here, but it is giving positive edge trigger after some time. So the time period got changed here. Look, they are reaching at the same time only. It is supposed to reach at t equals to t1, so it is reaching at t equals to t1 only, but the time period got changed here. So this is known as jittered clock. So here there is jitter. So this is known as clock jitter. Okay. So these terms will also be used. but not in our analysis. In our analysis, we are not going to use clock jitter, but we are going to use clock skew, that this will reach here at some early time, but this will reach after some time. So that we are going to see. Okay, but jitter will be rarely used. Okay, jitter will not be used that much, but you need to know the meaning. Okay, this much basics you should know. So these are the basics of VLSI, I would say, that setup time, hold time in any chip you design, whether you are an analog engineer or digital design engineer or digital IC design engineer, any IC design engineer, any chip you will design, there will be some digital blocks as well, there will be some analog blocks as well. So digital blocks also analog engineer only design. So there you will see that setup time violation will come, hold time violation will come, how to reduce that for that you need to add another block. If you are adding another block, then there will be parasitics. If parasitics are coming, then speed is becoming slow, but you need to design a high speed circuit, so for that you need to add another block. So these kind of problems come when you go into the industry. So these kind of terms will be used there: setup time, hold time, then clock jitter, clock skew. So what is the meaning of that you need to know. Okay, now let's come back to our topic now. Okay, but before that, just one more term, that is clock to queue delay. Clock to queue delay is nothing but propagation delay only. Okay, it is nothing but propagation delay, just it is the other name of propagation delay, nothing else, but it is used only for flip-flops. Clock to queue delay, what does that mean? That going from here to here, how much time it will take. So let's understand why this is an example. So take initial condition q equals to 0, clock to queue delay is 3 nanosecond, you need to draw the waveform at q. T equals to 1, that means it is in toggle mode, right? This is in toggle mode. Toggle mode means what will be your q plus? Q plus will be equals to q bar. Okay, so just as q initial I am taking as 0, just as the positive edge arrives, what it will say? Toggle now, go to 1. But what my flop will say? That yes, I will go to 1, but I will take 3 nanosecond of time. So I will take 3 nanosecond of time. Now just as the clock comes, just as the positive trigger comes, what it will say? Toggle now, go from 1 to 0. What your flop will say? Yes, I will go from 1 to 0, but I will take 3 nanosecond of time more. So here this was 3 nanosecond. So this was 3 nanoseconds. So it is just the propagation delay only. Okay, but in terms of flop, we call it flop or flip flop. In terms of flop or flip flop, we call it clock to queue delay. Sometimes I will call it propagation delay as well. So you need to understand he is talking about clock to queue delay only. Okay, so like collectively I will be using, sometimes I will be using propagation delay, sometimes I will be using clock to queue delay. Okay, so you should not be getting confused when this term comes. That's why I just wrote this down. Okay, otherwise everyone knows what do you mean by propagation delay, because this much basics we have already seen, right? Let's solve a question. This question is given in front of you. This is not visible, right? Now it is visible. Yeah, so what they are saying, a clock is given, input is changed from 0 to 1 at 3 nanosecond. Input is changed from 0 to 1 at 3 nanosecond, and after that it remains constant. Okay, so it is changed at 3 nanosecond. That means before 3 nanosecond it was always 0, and after 3 nanosecond it was always 1. Okay, so for proper operation, what should be the minimum clock time period and what should be the maximum hold time of the flip-flop? The setup time is given, that is 4 nanosecond. Forget about setup time, hold time. What do you mean by proper operation? What do you mean by proper operation? If this waveform is given, that is the D waveform, and this clock is given, and I am asking you to draw the output. Forget about setup time, hold time. Forget about anything. I am just asking you to draw the output. How will you draw it? You know how to draw it, right? How will you draw it? How will you draw the proper output? What is Q plus here? Q plus is equals to, what is Q plus? Q plus is equals to D, and that is equals to input. So it will just follow the input, nothing else. So it will be starting from 0. It will be starting from 0. At positive edge, what does it see? At positive edge, what does it see? 0 only. So it will sample 0 only. It will sample 0 only. Now at this positive edge, what does it see? 1. So it will sample 1. At the next positive edge, what does it see? 1 only. So it will always keep on sampling 1 only. So this is your proper output, right? This is your proper operation. But there are setup time, hold time, and everything is present now. Okay. Now at this positive edge, what clock will say? That I will look back and front. I will look back and look ahead. If I look back, 0 should be stable. Here you are having 0. The 0 nanosecond is the time. Okay, this is not the input. 0 nanosecond is the time. So I will look back and look ahead. So this 0 should be stable for the given setup time. What is the given setup time? Given setup time is 4 nanosecond, but this 0 is stable for infinite time, right? The input was always 0. That's why I have shown by dot. What they are saying in the question is that the input is changed from 0 to 1 at 3 nanoseconds. That means for less than 3 nanoseconds, it was always 0. Are you getting this point? So there is no issue about the setup violation. So you don't need to think about setup violation. But it will say that yes, I will sample 0, but my input should be stable for the given hold time. Now I don't know what is my hold time. They are asking you what should be your hold time. What should be the maximum hold time of the flow? Let's just say if my hold time is 2 nanosecond. If my hold time is 2 nanosecond. This is what I am assuming. Okay. So what this clock will say, what this positive edge will say, that this input 0 should be stable for next 2 nanosecond. Yes, it is stable. There is no hold violation. No need to worry about it. Okay. If it was 2.9 nanosecond, then what it will say? If it was 2.9 nanosecond, then what it will say? The clock will say that it should be stable for upcoming 2.9 nanosecond. Yes, it is stable. No issue. If it was 3.1 nanosecond, what clock will say? That it should be stable for upcoming 3.1 nanosecond. But is it stable for upcoming 3 nanosecond? Yes, stable, stable, stable. But here, this will be your 3.1 nanosecond, right? But here it is changing. And if it is changing, that means there will be hold violation. So what is your maximum time of hold? Like what is your maximum hold time? So your maximum hold time should be less than or equals to 3 nanosecond. Are you understanding this point? You just stand here, what you will do? You will look back and look ahead. If you are looking back, you saw that okay, there is enough time. Setup time, there is no chance of setup violation. If you are looking ahead, what you got to know? That after 3 nanosecond, my input is changing. So that means my hold time should be less than 3 nanosecond so that it can sample 0 perfectly. Otherwise, it would not be able to sample 0 perfectly, right? If it is stable, then only it would be able to sample the 0 perfectly. Now you will come here. What you will say? What this clock will say? That my input should, I will look back and ahead. If I look ahead, what do I see? That my input is always stable. For infinite time, it is always at 1 only. For infinite time, it is always at 1. So there is no issue about hold time. But if I look back, from here, if I look back, so what do I see? That for this much of window, my input is stable. Now my given setup time is 4 nanosecond, okay? My given setup time is 4 nanosecond. Let's just say if this time was 3 nanosecond only. This window was 3 nanosecond only. Then what would have happened? If this window was 3 nanosecond only, then clock would look for 4 nanosecond because given setup time is 4 nanosecond. Given setup time is 4 nanosecond. Clock would look back for 4 nanosecond, right? This clock would look back for 4 nanosecond. So here it will be looking. And here what it will see, that here it was 1, 1, 1, 1, then it is becoming 0. So setup violation is there, right? Now if this window was 5 nanosecond, let's just say if this window was 5 nanosecond. If this window was 5 nanosecond. So what clock will be doing? Clock will be looking for 4 nanosecond only. Here clock will be looking for 4 nanosecond only because setup time is 4 nanosecond. So clock will be looking for 4 nanosecond. So 4 nanosecond will be somewhere here. 4 nanosecond will be somewhere here. So here it was 1 and for all the time it was 1 only. So there is no setup violation. So what did you understand here? That clock need at least 4 nanosecond of margin. Clock need at least 4 nanosecond of margin here such that your input is remaining stable for previous 4 nanosecond. Your clock needs the setup margin that once this clock edge is arriving, before that your input should be stable for the given setup time. Are you getting this point or not? Now this input would know that I will change, but input also knows that clock edge will also come, and input knows that what is the demand of clock edge. Input knows what is the demand of clock edge. What is the demand of clock edge? Clock edge will say that you should be stable for the given setup time. So he knows that the clock edge will arrive after some time. Clock edge will arrive after some time, but I should be stable at least for 4 nanosecond. So from here, I am staying stable for 4 nanosecond, and here the clock edge is arriving. So this is your, what do we say? This is your threshold. Like this is the least requirement, right? So what will be this complete window? From here to here it is 3 nanosecond. 3 plus 4, this complete window is 7 nanosecond, right? So your T clock should be greater than or equals to 7 nanosecond. So that's it. This is your answer. Okay. This is your answer for T clock. This is your answer for hold time. Okay. The whole chapter will run around this only. Okay. This is very, very important. I hope you are understanding it. Let's understand it once again. So input was changing in this manner, 0 to 1. Okay. I look at this clock. If I look at this clock, then what will happen? It will look back. For a very long time it is stable. For a very long time it is stable again, right? If it is looking back and looking ahead, it knows that input 1 is stable. So there is no setup violation, no hold violation. Only the problem is here. So here there was no problem of setup. There was no problem of setup because 0 was stable for a very long time. But here there was a problem of hold. What this clock is will say that your hold time should be less than or equals to 3 nanosecond. Your hold time should be less than or equals to 3 nanosecond because I want my 0 to be stable for the next 3 nanosecond at least. So if 0 is stable for your 3 nanosecond only, that means certainly your hold time should be less than 3 nanosecond. Now what this clock edge will say that I don't have any problem with hold time because it is stable for a very long time. But I might have the problem with setup time. So the setup time is 4 nanoseconds. That means at least this much window should be 4 nanosecond. If it is more than that, it is good. But least requirement is 4 nanosecond because if it is 3 nanosecond, then I would go back and here I will reach. If it is 3 nanosecond, then my 4 nanosecond will reach here. From here to here, my 4 nanosecond will reach here. That means here my input was 1 and here my input is 0. So that will fall into setup violation. Okay, and that I don't want. So at least this much of window I need to provide. That if my input is changing, it should change in a manner that at least it should provide a window of setup time such that when the clock edge arrives, the clock edge should get a window of setup time. Are you getting this point? These are very confusing point. If I directly write down TSU, TH, then it would be very confusing. But we are taking the example. From very small example, we will build up and in the end you will be very comfortable. Believe me. But I hope till now you are following it up. You are following? Let's go to the next example now. Okay, we will just write down a formula, but from where this formula is coming, that we will see here. Okay, how this formula is derived, that we are going to see. So that is the important part. Now what is happening here? This is one flope, this is another flope. Output of this flope is fed to the input of this flope, and this is your output. These two are the clocks. Both are given at the same time. Both flopes are having the clock at the same time. Across this flope, this I am calling as flope 1, okay, and this I am calling as flope 2. Flip flop, basically I am calling it flope. So in flope 1, the input is always stable. Say yes or no. So will there be any setup violation or hold violation? At flope 1, the input is always stable. So will there be any setup violation or hold violation? No. So certainly there will be no setup violation or hold violation. No setup violation. Whatever the spelling is, yeah. Violation. No setup violation. No setup or hold violation. But the issue is here. Because the input of this is not stable, it is coming from this Q naught. So what is your Q naught plus? Q naught plus is equals to D naught, that is equals to 1 only. And what is your Q1 plus? Q1 plus is equals to Q naught. So let's draw the timing diagram. Things will be more clear to you once we draw the timing diagrams. So this is my D naught, which is always stable. This is my clock at flope 1. This is the clock at flip flop 1. Okay. So what will be my Q naught? This is my Q naught, which is 0 initially. Now there are some delay as well. There is a clock to Q delay is 2 nanosecond. Now at this clock, at this edge, what it will say? That follow D naught. That means you should go 1. So Q naught will say that yes sir, I will go 1, but I need the time of 2 nanosecond. So yes sir, I will go 1, but after 2 nanosecond. So I am going 1 after 2 nanosecond. Say yes or no. So it will be 1 after that, because always it is 1 only. So this took the window of 2 nanosecond. Now let's talk about flope 2. Flope 2. Now what is the task of flope 2? That it will sample this Q node data. At positive edge, it will sample this data. So what it will say? That yes sir, at positive edge, yes sir, I will sample this data, but I will look back and ahead. Why this was not looking back and ahead? This was also looking back and ahead, but it got to know that it is always stable, so no need to worry about that. But this will look back and ahead. If it is looking back, it knows that 0 was always stable. But if it is looking ahead, then what it will say? That your whole time of second flope should be less than or equals to 2 nanosecond. Because if your whole time is greater than 2 nanosecond, let's just say if your whole time is 3 nanosecond, then I will look ahead for next 3 nanosecond. I will look ahead for next 3 nanosecond, and at 3 nanosecond, I see there is a change in the input. So your whole time of second flope, this we are talking about second flope now. This clock is fed to the second flope, not to the first flope. The job of first flope is done. Now we are talking about second flope. So hold time of your second flope should be less than 2 nanosecond. If it is more than 2 nanosecond, let's just say if it is 3 nanosecond, then we see a change in the input. But the condition is after the clock age, it should be stable for the next 3 nanosecond as well, if the setup time is 3 nanosecond. But let's just say if my setup time, if the whole time is 3 nanosecond, but let's just say if my whole time is 1 nanosecond only. If my whole time is 1 nanosecond, then what clock age will say? That I will look for 1 nanosecond more. If I look for 1 nanosecond more, what do I realize? That I am 0 here as well. So there is no hold violation. Are you getting this point? So my TH2 is less than 2 nanosecond. Look, we will write down the formula and you will be solving the problems within 10 seconds, I am telling you. But before that, you need to know the concept from where things are coming, because if they are framing some complex problem, then any day you can make the timing diagrams and write down your conclusions if some complex problem is framed. So that's why we are looking at small blocks. In the end, for the whole big block, I will write down a formula, and within just by looking at the circuit, you will be writing down the final answer. But before that, we need to see the derivation. So I hope you must have understood. Now, what this clock edge will say? That I will look ahead and back. Now, if it is looking ahead, it got to know that it is always stable. So no need to worry. When it looked back, what it got to know? That it is changing here. It is changing here. From 0 to 1 it is going. So what it will say? That whatever the setup time I am having, that much margin I require at least. My setup time is 5 nanosecond. So from here to backward 5 nanosecond, input should be stable. So this is the least requirement. If this window was 4 nanosecond only, what is the setup time? What is the setup time for this? What is the setup time for this? That is 5 nanosecond. Okay. And if this window was 4 nanosecond, then what would have happened? This window is 4 nanosecond only. Then what would have happened? This clock will see for 5 nanosecond. Then here it would see 1, 1, 1, 1, 1. But after 4 nanosecond, it is becoming 0. So that means input is changing. So what this guy will say? That at least I need a window of 5 nanosecond. At least I need a window of 5 nanosecond. Are you getting this point? So what should be your T clock? T clock, this is your T clock. Okay, we can make the sample data. How the sample data will look like? First it will sample 0, and then it will sample 1, and it will always be 1 only. So this is how the sample data look like. But this is not our target. Our target is to find the T clock and T hold. So this is the hold requirement. And what should be your T clock? So at least your T clock should be greater than 5 plus 2, 7 nanosecond. So that's the answer. Okay. So basically what is happening here? From here to here data if data reaches from here to here, how much time it is taking? 2 nanosecond. right? And after 2 nanosecond, it need a margin of 5 nanosecond more. So this much of clock cycle I require. So that we are going to see, we are going to write it down as well. But if I just have told you that 2 nanosecond and then 5 nanosecond margin more, then you would be getting confused. But here you can directly see 2 nanosecond and this as requires margin of 5 nanosecond more. So total margin it requires 7 nanosecond. Okay. Now try solving this question on your own. I will pause the video, turn on the charger. Okay. But you try to solve this problem on your own. What you need to do, the same question is there, draw the timing diagram and let me know what should be your T clock and what should be the whole time of this second flop. Okay. So let me know that. I will pause the video and then I will come back. Yeah. Okay. So I hope you must have attempted it. Okay. So let's try solving it. So both are given the clock at the same time. Just one new thing is there that I have introduced this 2 nanosecond delay more. Okay. So what will happen? There will be no change in Q naught waveform. The Q naught waveform will be same as this, right? At positive edge, it is supposed to sample. It will look back and look ahead. Always 1, so it will sample. But after 2 nanosecond, because Q naught will say that, sir, yes, I will sample 1, but I need a time of 2 nanosecond. Now, this data D1, when it will reach there, Q naught plus the delay of 2 nanosecond. Whatever the Q naught here is, Q naught plus the delay of 2 nanosecond, that will be your data at D1, right? Data at D1. Q naught plus the delay of 2 nanosecond more. So that will be your data at D1. Say yes or no. So 2 nanosecond plus 2 nanosecond. Let me make it better. So 2 nanosecond plus 2 nanosecond, this time window is 4 nanosecond. Now what is the job of flip-flop 2? What is the job of flip-flop 2? Q1 plus is equals to D1. So whatever that is at D1, it will follow simply, right? Whatever that is at D1, it will simply follow it. So when the positive edge comes, what it will see? Look back, look ahead. Looking back, it always knows that it is always 0, no issue. Looking ahead, what it gets to know? That after 4 nanosecond, it is changing. So what it will say? That your whole time should be less than or equals to 4 nanosecond, because if it is more than that, let's just say if my whole time is 5 nanosecond, that means at 5 nanosecond your data is changing. So that is an issue for me. Your data should be constant. So your whole time should be less than or equals to 4 nanosecond. If it is more than that, then there will be hold violation. Say yes or no. Okay. What this will say? It will look ahead and look back. Looking ahead, every time constant. Looking back, what it will say? What is the setup time here? 5 nanosecond. So it will say that I at least need a window of 5 nanosecond. That means your input should be stable for at least 5 nanosecond. Otherwise, if it is not stable for 5 nanosecond, then what? There will be setup violation. If this window is, let's just say if this window is 4 nanosecond only. If this window is 4 nanosecond, that means your input is stable for previous 4 nanosecond only. If this window is 4 nanosecond only, then what will happen? It will look back for 5 nanosecond. And 5 nanosecond will reach somewhere here, because from here to here this will be a 5 nanosecond. If this window is 4 nanosecond only, then another 1 nanosecond here as well. So it will reach here, and what it will see here, that data is changing, and if data is changing, that's an issue for me. So what it will say, that at least I need a window of 5 nanosecond. 5 nanosecond. So this much window is T clock. So what is your T clock? This is 0, 0, 4 plus 5. This is 4 nanosecond. This window is 4 nanosecond. 4 nanosecond plus 5 nanosecond. So that will be your T clock. So my T clock will be, at least it should be 4 plus 5, 9 nanosecond. Say yes or no. Okay. So these are the answers. Now what is the conclusion of that? Let's see the conclusion. Okay. Let me know if you are able to follow it or not. What should be my T clock? How I will write it? What I will do? What should be my T clock? How I will do it? First I will see the input here is stable. So no need to worry about this flop. The issue is here. Then I will see after how much time this input becomes stable. After how much time this D1 input becomes stable. First I will see that. So after how much time? This clock starts from here. So first it will go through TPD1. then T combination 1. Here we used buffer, right? Here we used buffer. Any other combination circuit can also be there. So it will start from here. It will see TPD1 plus T combination. So this input will become stable. So first it will go with the TPD1 plus T combinational. Now if this input has become stable, then also it requires at least setup time. It requires the margin of at least setup time. That's it. This is your T clock. And what is your T hold? T hold of second, because T hold of first is of no use. T hold of second. So T small I will write. It will simply be, less than that. Which less than that? Just this setup time will not come. TPD1 plus T combinational. Why is that so? We have already seen in the example that the input here, that means my D1 input is becoming stable after 2 plus 2, 4 nanosecond. 2 plus 2, 4 nanosecond. And I should have the margin of maximum 4 nanosecond. So your whole time should be maximum 4 nanosecond. If it is more than that, if it is more than that, if your whole time is, let's just say 5 nanosecond, then there is an issue because your input is changing. So how will you remember it now? The thing is, first I will see this is constant, so no need to worry about that. Worry is this. So from here, how we are reaching? We are reaching from here to here. So first my clock will go here. It will see TPD1. It will have to go through the TPD1. Then it will have to go through T combination 1. Then after that it needs the T setup time as well. So T setup time margin as well. PD, or you can say clock to Q. This can be shown as clock to Q as well. T clock to Q. Okay. Clock to Q, T combinational plus T setup of this. There you go. And to avoid the hold margin, what should be the condition? Just remove this. Don't use setup. Just remove this. Okay. Just remove this. And in the worst case, if you get confused, this we have. Draw the timing diagram and everything is right in front of you. Okay. But you will not be getting confused. We will see more example now. I will make more troubles. What I am going to do? Now I am going to introduce clock skew. So this block was already there. These were already there. Now what new I have done? This new I have done. The same question is there. Try doing it on your own. Just the clock is changed now. This guy will get the clock after 1 nanosecond. Okay. For this you can watch the solution. For next one you will try on your own. So this guy will get the clock after 1 nanosecond. Otherwise everything is same. All the things are same. Data was stable here. No need to worry about. At flop 1 data is stable. So no need to worry here. Right? Data is always stable. So no setup violation, no hold violation. It will simply sample it. But what it will say that I need a time of 2 nanosecond. So it will be 1 after 2 nanosecond. And at D1 the data will reach at 4 nanosecond because 2 nanosecond more delay is there. So 2 nanosecond more delay is there. So it will reach here at 4 nanosecond. Now what will be the clock at flop 2? This is your original clock, which is being given to flop 1. At flop 2, the clock will reach after 1 nanosecond of delay. So after 1 nanosecond of delay, it is reaching here. Okay. So now what it is going to do? When the positive edge comes, what it will say? That I will look ahead. And how much margin do I need now? This clock is ahead now, right? How much margin it needs? 3 nanosecond. So my TH2 should be less than or equals to 3 nanosecond. If it is more than 3 nanosecond, let's just say if it is 4 nanosecond, then what will happen? 1 plus 4. If my TH2 is 4 nanosecond, then what will happen? 1 plus 4. That means at 5 nanosecond I will reach. And at 5 nanosecond input is changing. So you just need this margin. Okay. What is this point? T clock plus 1 nanosecond. Say yes or no. And what it will say? Just as the positive edge arrives, for the previous setup time, for this much of window, my input should be stable. And what is this window? This window is equal to setup time, which is 5 nanosecond. That means this clock edge requires a margin of 5 nanosecond. So input should be stable at least before 5 nanosecond. At least before this 5 nanosecond. Right? So tell me one thing. This time is T clock plus 1 nanosecond. Say yes or no? T clock plus 1 nanosecond. This should be greater than or equals to what? 4 plus 5, 9 nanosecond. Do you agree to this point? Are you understanding this point or not? Look, this window is 3 nanosecond. And this window is 5 nanosecond. And this complete window is T clock. Say yes or no? So you can either directly write that your T clock should be greater than or equals to 3 plus 5, 8 nanosecond. Either you can directly write it, or you can take the reference of 0. This complete line shows T equals to 0 nanosecond only, no? This is 0 nanosecond, this is 0 nanosecond. So if this is 0 nanosecond, this is 1 nanosecond, and this window is T clock, so this will be T clock plus 1 nanosecond, right? Now if this is 0 nanosecond, this is 4 nanosecond. We saw it here that there is further delay of 2 nanosecond more. So 2 nanosecond plus 2 nanosecond, this will be 4 nanosecond. 4 nanosecond plus 5 nanosecond. So this point will be 9 nanosecond. So your T clock plus 1 should be greater than 9 nanosecond. So from there you will get to know that T clock should be greater than 8 nanosecond. Simple mathematics I am using, nothing else. This was delayed by 2, this was delayed by 4, then it was stable for next 5. It was stable for next 5. So T clock plus 1, this was T clock plus 1 with respect to 0. So T clock plus 1 with respect to 0. This much time is 4 nanosecond, this much time is 5 nanosecond. So T clock plus 1 nanosecond should be greater than 9 nanosecond. So T clock should be greater than 8 nanosecond. Okay. Now let's write down the conclusion. What is the conclusion you see? Input is fixed here. No need to worry about it. All you need to worry about this. Okay. So what should be your T clock? T clock should be greater than, you go from here to here. How much delay you need to see? First you will go through TPD1. Look, setup time and hold time are not any delay. They are the parameters. They are not any delay. So first we are calculating the delay, that when it becomes stable. So T setup, sorry, not T setup, sorry, T propagation delay, or you can say clock to key delay, plus T combinational circuit delay. This much time it requires, plus it needs to be set up before, because once the clockage arrive, it will see that it should be set up for a particular time. So plus T setup of 2 minus T skew. You can see here, this T skew was getting subtracted. This was the T skew, no? 1 nanosecond. This is the 9 nanosecond time, which is this 9 nanosecond time. 2 nanosecond plus 2 nanosecond plus 5 nanosecond minus this time. See the waveforms. You can see the waveforms, okay? 2 nanosecond plus 2 nanosecond, 4 nanosecond, 4 nanosecond plus 1, 5 nanosecond. But this is your T clock window, because T clock is ahead, 1 nanosecond ahead. So it feels like that this is 9 nanosecond. Answer should be 9 nanosecond. Answer should be this. No. But clock is also ahead, no? So how much time clock is ahead? That also we need to subtract. So minus T skew. Eventually you are going to remember it, okay? Just one more block has been added. From here to here we were already doing. We are going TPD plus T combination minus T skew. So this skew I need to eradicate. This analysis I have given just because if some tough question comes, so at that time you should be able to answer it, okay? Now, what will be your TH2? Your TH2 should be greater than or equals to TPD1 plus T combination. I just told you one thing, that this will never come. In TH2, this thing will never come. That's it. Minus T skew. Okay. That's it. This is for TH2 and this is for T clock. You can practically think as well that this will be stable at that time, and T setup should more margin I need to have, and I have to subtract T skew because this clock has been going ahead. This clock has been going ahead by T skew. So whatever the margin I require here, from the next positive edge, whatever the margin I require from the next positive edge, whatever the margin I require, that should be subtracted by this T skew. Say yes or no? Okay, the complete margin will be starting from 0 to here, but that should be subtracted by this T skew, and in the waveform directly we can see it. Okay, if nothing goes, like if you are not able to catch up any question, still you will be able to solve it because you know how to draw the waveform. Very easy waveforms are there, right? Let's make your trouble more, what I am going to do, I am introducing one more delay here. So that's the worst case. One more delay we have introduced here. So this clock is also 2 nanosecond delayed. This clock is also 1 nanosecond delayed. Here you are having a delay of 2 nanosecond, and then you need to find what should be your T clock and what should be your hold margin for this particular flow. Here input is fixed. Here input is fixed, so no need to worry about that. Try writing it directly. First try writing it directly, then try writing it using the using the timing diagram. After that you can write down the conclusion as well. So try writing it directly first. What do you think? What should be the answer? What I told you, that I need to find the time till this becomes constant, because here input is constant, no need to worry about it. So when this will become constant, first it will go through the delay of 2 nanosecond, then another 2 nanosecond, then another 2 nanosecond. So it will be constant at 6 nanosecond minus this 1 nanosecond. That's it. This will be your T clock. Okay, let's not write it directly. Let's do it using our waveforms. So first we will do it using our waveform, and in the end we will write down the conclusion. So these are the waveforms which you can draw on your own. This is the clock at float 1, 2 nanosecond. Then Q naught. So it will reach, clock is reaching, this is the clock at float 1. This is the original clock, normal clock at float 1. After 2 nanosecond it is starting. Then 2 nanosecond more delay is there. At this edge the clock will tell that follow the input. So Q naught will say that yes sir, I will follow the input, but I need 2 more nanosecond. So that means this window will be 4 nanosecond. This time will be 4 nanosecond. I can show that this window is 2 nanosecond. So I need 2 nanosecond more. Okay. What will be D1? Then D1 will be 2 nanosecond more delayed. So D1 will be 2 nanosecond more delayed. So this window is 2 nanosecond. And this time will be 6 nanosecond. So D1 is 2 nanosecond more delayed, right? And what about clock at float 2? This will be the clock at float 2. Now what this clock will say? That your input should be stable after this much of time. Basically this should be your hold time. So maximum you can have the hold time of 6 minus 1, 5 nanosecond. Maximum you can have the hold time of 6 minus 1, 5 nanosecond. Or what about T clock? So before the next positive edge arrives, at least I need a margin of how much time? At least I need a margin of setup time. And what is the setup time? That is 5 nanosecond. At least I need a margin of 5 nanosecond. So how much is this time? So this window is 11 nanosecond. This is your 11 nanosecond, right? 5 plus 6, this was your 0. 5 plus 6, 11. What this will be? Tell me. This will be your T clock plus 1 nanosecond. Why is that so? Because from here to here it is 1 nanosecond and this is your T clock. So T clock plus 1 nanosecond. So T clock plus 1 nanosecond. T clock plus 1 nanosecond should be greater than or equals to 11 nanosecond. So T clock should be greater than or equals to 10 nanosecond. Okay. So that's the answer. What is the conclusion now? So what did I tell you? Here input is fixed, no need to worry about that. The input is changing here, so worry about this. Okay. So I will see when it reaches here. So when it reaches here, for that what I am going to write? So my T clock should be greater than, how much delay it needs to go through? First it will go through the delay of this T skew 1 plus TPD1, only the delays I am writing, plus T combination 1. Just as it is stable here, it needs a margin of setup time as well, plus T setup, it needs a margin of setup time as well, minus this T skew. The formula which feels like very complex has become very easy for you because you know what you are doing, right? You are moving ahead in the path. You are going from flip-flop 1 to flop 1 to flop 2. I am going from flop 1 to flop 2 because the input at flop 1 is stable, so I don't need to worry about that. So I am going from flop 1 to flop 2. So T skew plus TPD1 plus T combination plus T setup 2, this much margin I require, minus this T skew 2. Okay, the same thing we have done. All the delays plus the margin, all the delays that is 6 nanosecond plus the margin minus this 1 nanosecond. All the delays plus this margin that is 11 and minus this 1 nanosecond. This is what we have done here, right? And what about TH2? I told you one thing. What did I tell you? Just don't write this setup, rest all will be same. So T is Q1 plus TPD1 plus T combination minus T skew 2. Basically, all the delays, forget about the margin, forget about the setup margin, all the delays, this is the all delays minus this thing. So this is your hold time, which is 1 minus 5, sorry 6 minus 1, 5 nanosecond. All the delay minus 1 nanosecond, that is 5 nanosecond. So this is how this complex circuit is taught. Like usually it is taught that this diagram they will make and they will write these things. So people will be getting confused, right? But now we have seen the timing diagram, we have seen the core depth of this particular concept, that from here to here we are going, then we need a setup margin, and since my clock is more delayed, so I will subtract this. And for whole time, I will need all the delay, but I don't need setup margin there. My clock should be ahead of that. Sorry, my clock should be behind that. My clock trigger should be behind that. So that much margin I need. Okay then, so let me take a pause, drink some water, and then we will proceed in this particular video. Okay, so I will take a pause now. Yeah, so let's continue our video. So this example we have seen, this conclusion we have seen, right? Now we will see this condition. If both the inputs are not fixed, in all the examples what we were seeing that this input was fixed here, all the examples we saw this input was fixed, right? But here this input is also not fixed. So how will you analyze that? How will you analyze that? Look, what you can do, assume this as fixed. Assume my D node is fixed. At some point it would be fixed only. So assume this as fixed. Then go from flop 1 to flop 2. Write down the T clock and TH. Then assume D1 to be fixed and go from clock 2 to flop 2 to flop 1. Basically this is your flop 1 and this is your flop 2. In previous examples, you could only go from flop 1 to flop 2, right? This was the only path. Can you come from flop 2 to flop 1? No. There is no path that I can come from flop 2 to flop 1. But here, I can go from flop 1 to flop 2 as well. And I can come back from flop 2 to flop 1 as well. Say yes or no. Right? So I have two paths here. So first what I will do, if I am going from flop 1 to flop 2, here what we were doing, I was going from flop 1 to flop 2. So here my data was constant. So what I am going to do, here I will go from flop 1 to flop 2 and I will assume this is constant. So I am going from flop 1 to flop 2. So what I will say, if I am going from flop 1 to flop 2, this is the first condition, then data, or I should write input at flop 1 is constant. So now I am traveling from here to here. How I can write down the T clock value? Tell me. You will write down on your own. If you are going from here to here, first it will have to go through this T skew. So T skew plus, then it will have to go through this TPD plus TPD, PD1 plus, then it will have to go through this T-comb1, T combination 1. Then your input would become stable here, but it needs a margin of TSU2 minus this clock skew, right? The clock skew which is fed to this flop minus T skew 2. This is your 1, should be clearly written. This is your 1. So how did I write that? I went from here to here till here, then it was stable here. I need this margin minus this. Say yes or no. So this is my T clock. And what is my TH2? T clock should be greater than this, and for TH2 it should be less than. Just you need to eradicate this TSU2. So T skew 1 plus TPD1 plus TCOM1 plus TSU I need to ignore. So minus T skew 2. That is the answer for hold time 2. Now I can go from flope 2 to flope 1 as well. Flope 2 to flope 1. So if I am going from flope 2 to flope 1, flope 2 to flope 1, that means I will assume that this data is constant now. So data at input at flope 1 is constant, that means D1 is constant. Here what I will assume, that input at flope 2 is constant. That means D2 is constant. So how will I write it? T clock. Try writing it on your own. T clock should be greater than or equals to. You are going from here to here, right? So basically you will start from the clock, you will walk in this direction. When you are going from 1 to 2, how did you start? Started from the clock, went here, saw the margin and subtracted this. From here if you start from the clock, go here, reach here, see the margin, subtract this skew. Skew of the flope where you are reaching. Skew of the flope where you are reaching. So first we subtracted skew 2, now we are going to subtract skew 1. So I will start from here, I will first reach here. So T skew 2 plus TPD2, T skew 2 plus TPD2 plus T combination 2, right? T skew 2 plus TPD2 plus T combination 2. Here I have reached now. Then I need the setup margin of this plus T setup 1 minus I will subtract the skew of this minus T skew 1. So that will be my T clock. Okay. So I will write this as, this I am writing as T dash, this I am writing as T double dash, this I am writing as T dash H2. Or now what about, why I should write T dash H2? I should write TH1 TH2 only. And what about TH1? What about TH1? So TH1 should be less than or equals to T skew 2. Here I will be writing TH1, right? Because in these phases I was going here, so from flope 1 to flope 2 I was going, so TH2 I was writing for this one, because I here this data was constant, right? This data was constant. Now I am assuming this data is constant. So if this data is constant, there is no meaning of hold and setup here. All meaning of hold and setup we will look here only. Are you getting this point? Did you understand this point? If this data is constant, there is no meaning of this setup and hold. So I will be writing the whole time of this flope. When I was going from here to here, when I was going from here to here, I was writing the setup of this flope. Now if I am going from here to here, so I will write down the setup of this slope, no? So TH1, so TH1 plus TPD2 plus TCOM2, setup should not come, so minus T skew 1. Say yes or no? Now these are two different values, so no need to worry about that. Now this guy is saying that T clock should be this, and this guy is saying that T clock should be this. So whose you will listen to? What do you think? Let's just say if this answer is coming that your T clock should be greater than 11 nanosecond, and here this answer is coming that your T clock should be greater than 13 nanosecond. So which you will listen? Think about it. T clock should be greater than 13 nanosecond, right? Are you getting this point? Let's keep it here as it is. If T clock is coming, this guy is saying that T clock should be greater than 11 nanosecond. If I say X is greater than 5 and X is greater than 7, then 6 will satisfy it? No, because 6 is less than 7. But if I say X is 8, so 8 is greater than 5, 8 is greater than 7, so 8 is correct. So you always need to take the maximum limit, no? So this guy is saying that clock should be greater than 11 nanoseconds. This guy is saying that it should be greater than 13 nanoseconds. So what would be the final answer? 13 nanoseconds, right? So let's keep it here only. You will understand that what will be your final answer based on the question. Now what will happen is that a lot of guys will not be able to digest that how this formula came, how these things are coming. So what you can do, you can draw the timing diagram. It will be very complex. What you need to do, I will tell you what you need to do. Give the same thing, all these values are there, assume all these values, but assume the initial condition as 0 and 1. Assume that my initial Q0 output is 0 and Q1 output is 1. Because if you assume 0, 0, then what will happen? 0, 0 will keep on going. Input will not even change. Are you getting this point? So this will be acting as your ring counter. This is just a ring counter only. Assume this as 0, this as 1. Draw the waveforms. Take all the conditions. Then you will realize that these two conditions will only come. These answers will only come. So I have also done it. Okay. For me also it was very tough to digest. But then also in the rough notebook I did this analysis. It will be very complex to teach it here. And no one is going to ask you. Okay. This is very rare that they will ask you this combination. Very rare. But what if they ask you? Then if output is connected back to the input. So what you need to do, you know that there are two paths. I can go from flop 1 to flop 2 as well and flop 2 to flop 1 as well. If I am going from flop 1 to flop 2, then I will assume that my data is constant here, flop 1 to flop 2. Okay. Assuming the data constant here, flop 1 to flop 2 I will go. I will see over the delay, setup margin is there, that I will take in action, and then I will subtract this skew. That's it. Okay. And if I am going from flop 2 to flop 1, then what I will do? I will take all the delays, see the setup margin, and just subtract the skew of this particular clock. Okay, so that I am going to do. So this have been derived, okay, and you can check as well. But the condition you need to take, that initial condition you assume 0 and here you assume 1. Okay, then you will get to know that this will keep on flowing in this particular loop only. Like if this is 0 and this is 1, then it is simply this 1 will come here, this 0 will come here, then this 0 will come here, this 1 will come here. So this waveform you will get, this will be a mode 2 counter. This will be a simple ring counter, and you will draw the waveform and you will realize how much hold margin you require, how much setup margin you require. Sorry, how much hold margin you require for flop 2, how much hold margin you require for flop 1, and how much clock you require. So that you will get to know once you draw the waveforms. If you want to draw it, then you can draw it. No one will ask you in the interview, neither in your gate examination. They can simply ask this final expression, and that you need to write, and that I have told you how to write. Okay, because we know that there are two paths, so we will follow both of the paths, flop 1 to flop 2, flop 2 to flop 1. So this was the question that was asked in GATE 2020, I guess. Okay, so let's solve it. Here what do I see? I can go from, I see these inputs, flop 2 input and flop 1 input. I see both are not constant. Then certainly there has to be path that I can go from flop 2 to flop 1 and flop 1 to flop 2. Say yes or no. So from where this data is coming? This data is coming from this particular path. So first I will go from flop 1 to flop 2. Let's go from flop 1 to flop 2. So if I am going from flop 1 to flop 2, how I will go? I will start with clock. Flop 1, this is flop 1. I will assume the data is constant here. I will start with clock. TPD plus these delays 4 nanosecond plus I will reach here. Data is constant. I need setup margin. Skew is not there, so skew I don't need to subtract. If skew was there, let's just say some skew was there. If some skew was there here, I would have subtracted it. Skew of flop 2. Skew of flop 2 I would have subtracted, right? But no skew is there, so I am not going to subtract it. I hope you are able to follow. So T clock should be greater than or equals to 3 nanosecond plus 2 nanosecond plus 2 nanosecond. We have reached till here. Now my data is constant. I need 4 nanosecond window more. So my T clock should be greater than or equals to 5, 7, 11 nanosecond. Okay. Now I will work from flop 2 to flop 1. So what should be my T clock? Flop 2 to flop 1. Flop 2 to flop 1. I will start with clock. I will reach here and simply I will see the setup margin. So what I am going to do, if I am starting from here, 8 nanosecond. Directly I have reached here and see the setup margin, that is 5. So 8 plus 5, that is, what is that? 8 nanosecond delay plus I have reached here, so I will see the setup margin, that is 5 nanosecond. So 8 plus 5, what that would be? So T dash I can call it, T double dash I will call it. So this guy is saying that it should be greater than 13 nanoseconds. So whose you will listen? You will listen to this guy, that your T clock should be greater than or equals to 13 nanosecond. So what they are asking, maximum frequency, maximum clock frequency. So your F clock should be less than or equals to, here this is the final answer, that is this, and your F clock should be less than or equals to 1 by 13 nano. Okay, so nano means 10 to the power 9. I don't have calculator, so 1000 by calculator 1000 by 13. So F clock is coming out to be 76.92 megahertz. Okay, so that was the answer, 76.92 megahertz. So that was the answer. This is how you need to solve it. Well and good. Let's see this question. Try thinking on your own. For proper operation, maximum allowable clock frequency. What should be clock frequency? Try thinking on your own. Don't go blindly. Which type of counter it is? Asynchronous counter. In case of asynchronous counter, all inputs are fixed. Why is that so? Because they will be working in toggle mode. All inputs are fixed here. If all inputs are fixed, then do you need to worry about your setup time and hold time? So these guys will not even be used. Say yes or no. If you are getting confused, let's draw the timing diagram. Okay, let's draw the timing diagram. This is your clock and all are in toggle mode. That you agree, right? All are in toggle mode. All are in toggle mode. 1 is there, so all are in toggle mode. So how will the waveform look like? 2 nanosecond, 3 nanosecond and 4 nanosecond. Sorry, 3 nanosecond delay, 2 nanosecond delay and 3, 2, 4. So first is having 3 nanosecond delay. Okay. What will happen is that, how will I make the waveform of Q naught? With the rising edge of clock, what Q naught will say? That you need to toggle, but I will take the time of 3 nanosecond. Now, with the rising edge of Q naught, this will say, with the rising edge of Q naught, this flop will say that I will toggle, but I need a window of 2 nanosecond. This example we have already seen when we were studying asynchronous counter. We are just revisiting it. So yes, I will toggle, but I need a time window of 2 nanosecond more. Time window of 2 nanosecond more. Already seen it when we were studying our asynchronous counter. So there we saw the concept of delay, right? But I just wanted to make sure that there is no use of setup time here. Now, when this will toggle, sorry, this waveform I made wrong, sorry. So this will toggle at the next rising edge, right? Here it will toggle. So 3 nanosecond. It doesn't feel like that this is 2 nanosecond, but let's assume it. So this is the rising edge. Now when Q2 will toggle, Q2 will say that I will toggle at the rising edge of Q1. I will toggle at the rising edge of Q1, but I need a time window of 4 nanosecond more. So this time window is already 5 nanosecond. So I need a time window of 4 nanosecond more. No, sorry, not time window. I should say I will toggle after 4 nanosecond more. So here I am going to toggle. So are you remembering the concept now? So this is 4 nanosecond. So this complete window is 9 nanosecond. So basically, to avoid the skipping count, do you remember what is the meaning of avoid the skipping count? If your T clock is less than 9 nanosecond, then you will skip some counts. That this is your, this what is this? This is your down counter. Right? Those who haven't studied it, those who are watching it on YouTube, I'm not sure if I'm going to upload it on YouTube, but those who haven't studied it, those who are watching on YouTube, they can completely design it and they can assume that if my T clock is less than 9 nanoseconds, then what will happen? You will skip some count. This is your down counter. That means you are supposed to go down from 002 to 111, then 110, 11, then 110, after that 101, after that 100, after that 011, after that 010, after that 001, and then again 000. So this is what you are supposed to go. But if your T clock is less than 9 nanoseconds, that means if T clock is less than that, then you will skip some count. You may miss 6 or you may miss 5, you are not going to miss 7, but you will skip some count. And there will be some glitches as well. So certainly there will be some glitches. And to remove those glitches, we use strobing. We studied the concept of strobing. We use a decoder where we use a strobe signal. I hope you remember it. Those who have studied asynchronous counter, they remember it, right? But if you don't remember it, then you should revisit it. And if you are studying from YouTube, then I hope you must have referred to some other resources where you must have studied the concept of strobing, how to use the strobe signal. But here the conclusion is that you do not need setup time or hold time. Just you know that here output will be reaching, the final output here will be reaching after 9 nanosecond, and your clock should be greater than 9 nanosecond, or you can say 3 nanosecond plus 2 nanosecond delay plus this 4 nanosecond delay. So your T clock should be greater than 9 nanosecond. That's it. So at least in this window, this 9 nanosecond should have been covered, because if this 9 nanosecond was ahead, here, then there will be an issue. You would skip this count 1 1 1. You would skip this count, right? That count will be skipped. So that's an issue. If that happens, then you will skip some count. So to avoid skipping count, you need T clock should be greater than 9 nanoseconds. There is no use of setup time and hold time because inputs are fixed. Okay, let's solve this question which was asked in GATE 2004. Maximum allowable frequency you need to dial. Setup time is written. The delay of this AND gate is written, and all these are written. Okay. First thing what you will see, fixed, 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 fixed. This is fixed, but this is not fixed. So if these are fixed, no need to worry about them. No need to worry about setup time and hold time. You just need to walk through them, and you need to reach here. The input which is not fixed, I just need to reach there. So I will start from this clock. I know one thing, that this will take me 15 nanosecond of time. No, this is how I will not be solving the problem. What I will see, that I need to stable this data, right? Now when this data will be stable, when these two inputs are stable, when this data will be stable, to make this data stable, these two inputs should be stable. Now when these two input will be stable, so if I am starting from here, this input is coming from this flip-flop. So when this output will come, if this clock starts, this output will come at 15 nanosecond, because T delay is 15 nanosecond. So this output will come at 15 nanosecond. And when this output will come, so this output is coming at 15 nanosecond, so certainly this output will also come at 15 nanosecond only. Now this 15 nanosecond is fed here, so when this output will come at 30 nanosecond. Did you understand this point? This will depend on these two inputs, and these two inputs are depending. This is the output of this, and this is the output of this flop. Okay, let's call it flop 1, flop 2, and flop 3. So input of flop 3 is depending on the outputs of flop 2 and flop 1. The output of flop 2 is depending on the output of flop 1, because that is the clock. 15 nanosecond clock is fed here. So that will come after 15 nanosecond, and after the delay of more 15 nanosecond, this will come out. So this is coming out at the delay of 15 nanosecond, and this is coming out at the delay of 30 nanosecond. So when this will come out, because this delay is more, so this guy will have to wait for this guy. You are calculating worst case delay, so this guy will have to wait for this guy, right? So 15, and here it is 13. Sorry, here it is 30. So 15 and this is 30. So 30 plus 5. So this will be stable at 35 nanosecond. And if this is stable at 35 nanosecond, that means it requires a setup margin again. So that is 5 nanosecond. You just made the input stable. So your T clock should be greater than, you go to know that it is being stable at 35 nanosecond. And then you require another 5 nanosecond margin. So T clock should be greater than 40 nanosecond. And what will be your maximum allowable frequency? That should be this 1 by 40, 250, right? 1000 by 40, 25. So F clock should be less than 25 megahertz. Okay, so that's the answer. Very easy, very straightforward problem. Okay, so yeah, that's it about this video. We will see more concept. This is not completed. We will see more concept, like this is a very small concept, just we can discuss here only. If this is ut, what is this waveform? Ut minus 3. Very simple concept of signal system, but this will be used. Why? Where this will be used? When this clock is positive as triggered. Now what if this clock is negative as triggered? So that you can take as an homework, draw the timing diagram of this and then come to any conclusion. You will get to know what will be your minimum required time period and what will be your, here I forgot to write what will be the whole time requirement. That you will get to know once you solve this using timing waveform. So solve it using timing waveform, then you will realize why did I do this, and then come to any conclusion. What conclusion you will come to, that I want to see. So this thing we are going to see in the next lecture. Okay, this question we will solve, more questions we will solve. So a lot of questions we are going to solve, and after that you will be more confident in this particular chapter. So I hope you are getting the good confidence. Till now, if you are not confident in this particular what do we say, in this particular topic or chapter, but now I hope you are getting the confidence. So let's meet you in the next video. There we are going to discuss more examples and more interesting things. Okay, thank you very much. Hi everyone, so now we are going to solve this problem. Seems like a very easy question, but the catch here is that this is negatively as triggered and this is positively as triggered. So first we are not going to apply any formula, anything like that. We are going to solve by basics. And what is the basics? We will draw the timing diagrams. Okay, so what do we see here? This input is fixed, D naught is fixed, and D1 is depending on Q naught. So your Q1 plus is equals to D1, which is equals to Q naught. So first I will draw this clock. The same clock is fed here. This is positively triggered, this is negatively triggered. Then I will draw this waveform as well, and then I will see how my Q0 and Q1 will go. So let's check that out. So this is my clock. Clock at slope 1 and clock at slope 2 both are equal only, right? Q0. How will my Q0 waveform look like? Q0 initially is 0. Just as the positive edge arrive, what it will say? Sample 1. But it has a delay of 2 nanosecond. So it will be sampling 1, but it will take 2 nanosecond of time. Okay. So it is sampling 1, but it will take 2 nanosecond of time. And then it will always be 1. Say yes or no. There is no meaning of setup time and hold time here. Why is that so? Because input is always stable. So this clock has no problem. No problem with setup time as well, no problem with hold time as well. Now, this input, basically this output, I would say, this output is fed as the input to this clock, right? Q0 is fed as the input to this clock. Now this clock is negatively edge triggered. So what it will do? It will say that at the it will say that at the negative edge I will see whether my input has been stable previously and after that. At the negative edge I will look ahead and back. If I am looking ahead, what do I see? My input is always stable. This is working as input, right? This is D1 only. So what do I see? This is always stable. But if I look back, what do I see? That I need a margin of setup time, right? If I look back, I know that my input is getting changed. So what is the given setup time? Given setup time is 5 nanosecond. Let's just say if this window is 4 nanosecond, then what I will see? That at this negative edge, this is 1, but I need to see till 5 nanosecond. I will go back and till 5 nanosecond my input should be stable. But if I go back at 5 nanosecond, what is the scene? That my input is at 0. So at negative edge my input was 1, here my input is 0. So this is the setup violation, and that condition I do not want. So what I am gonna do? I am gonna tell that at least I need a margin of setup time here. At least I need a margin of setup time. Say yes or no, which is equals to 5 nanosecond. So if this is 5 nanosecond, then what will I do? Here I would see that it is 1 and I will go back to 5 nanosecond. Here also I would see it is 1 only. It can be greater than 5 nanosecond if this margin was 6 nanosecond. If this margin was 6 nanosecond, then what I would have done? At negative edge, I would go back for 5 nanosecond. I would go back here for 5 nanosecond. What I would see? That yes, it is being 1 only. So there is no issue about that. So I need a margin of setup time here. Okay, that is 5 nanosecond. And what was this delay? This delay was 2 nanosecond, right? This delay was 2 nanosecond. So what did you see here? The interesting thing, what did you observe? First thing is that this much time is t clock by 2. And there is no hold violation. No hold violation at all. Why there is no hold violation at all? Because it is negatively edge triggered, and at negative edge, if it is looking ahead, what does it see? If it is looking ahead, what does it see? It sees that it is always stable. So there is no hold violation at all, right? What about the setup violation? What about this t clock? So your t clock by 2 should be greater than 5 plus 2 nanosecond. 5 plus 2 nanosecond. That means your t clock should be greater than or equals to 14 nanosecond. If I had blindly solved this problem, then what I would have done? That I would go from here to here. 2 nanosecond and then setup margin. Look, I would go from here to here. So what will be my t clock? T clock is greater than 2 nanosecond plus 5 nanosecond. So t clock should be greater than 7 nanosecond. This would be my answer if I was doing it blindly. But I know that there is negatively edge triggered. So there is some catch. So I solved it using timing diagram. But what is the conclusion I would make now? Okay, a very interesting thing will come. This was your positive edge clocked, okay, positively edged clock, and then there was this negatively edged clock as well, right? Can I take out this bubble? Do you remember how did we make negatively edged clock? Basically, this is your clock, okay? This is your positive edge clock, and this is your negative edge clock, post edge clock and neg edge clock. Now what do? I invert this, okay? I put an inverter. I invert this. So how it will look like? 1 to 0, 0 to 1, 1 to 0 and 0 to 1. What is the positive edge here? This is the positive edge. So can I say one thing? That positive edge and negative edge clock both are same. Positive edge clock and negative edge clock both are same. One is time shifted by t by 2. If this is 0, this is t by 2 and this is t. This is 0, this is no. Basically, if I time shift this, if I time shift this with the t by 2, what will happen? If I time shift this with t by 2, what will happen? This 0 will come here and 1 will come here. This 0 will move ahead. Basically, this 0 will move ahead here and then this 1 will move here. Are you getting this point? If I just time shift this, I just inverted it. What did I do? I just inverted it. Here there is negative edge, right? This is the negative edge. If I invert this clock and I say that I am triggering it at positive edge only, or I say that this clock is negatively edge triggered, both are same thing. Are you understanding this point or not? This is the clock, this is the negative edge clock. If I just apply an inverter here, if I just apply an inverter, this is how this clock will come. Now I am saying that I have applied the inverter, but still it is positively edge triggered only. What I mean to say is that negative edge triggered is positive edge triggered only. Just the thing is, there is in between there is an inverter, nothing else. Both are same thing. Both are same thing. Both are equivalent to each other. Both are same thing, just there is an inverter. So if I invert this clock and I say that still it is positive as trigger, there is nothing wrong. And how much phase shift this inverter is providing? Minus T by 2. Say yes or no. This inverter is providing minus T by 2 phase shift. Are you agreeing to this point or not? Are you able to understand this point or not? Look, we could have solved it using timing diagram, but I am telling you how to solve it quickly. Positive as triggered, negative as triggered. Okay. We saw this is your positive as triggered, this is your negative as triggered. But if I think that if I take this bubble out, that means I just need to invert this clock. I need to invert this clock and think it as a positive as triggered only. Think it as a positive as triggered. Do I satisfy the condition? Yes. So that means this inverter is just providing a phase shift of minus T by 2. If I shift this, let's just say if you shift this back by T by 2, what will happen? This 0 will come here, this 1 will come here, then another 0 will come here. So this waveform only you will get, no? So this inverter just provide a phase shift of T by 2. Do you agree to this point or not? Minus T by 2. It provides a phase shift of minus T by 2. Now someone can say that, sir, it provides a shift of plus T by 2 as well. Because both are same thing, right? It provides a phase shift of plus T by 2 as well. Because 180 degree and minus 180 degree both are same thing only. So you can say that, sir, it provides a phase shift of plus T by 2. Yes, it provides a phase shift of plus T by 2, but that is not useful for us, because when we write down the answer, it will create a problem if we take the phase shift as plus T by 2. That I will tell. Okay, no need to worry about that. That I will tell. So now what my problem becomes? What my problem becomes is that I was having this flow. This was fed with positive as triggered clock. Okay. Now, if this was fed with positive as triggered clock, then I know the shortcut how to write down the final answer. Just walk from here to here and then you can write down the final answer, right? And even if there is a clock skew, then also there is no problem. Say yes or no. So what I can do, which was negatively as triggered, so I could make this as something like this. I could just take out that bubble and I can call that this will provide me a phase shift of minus T by 2. Do you agree to this point or not? That bubble I am taking out and telling that this is providing me a phase shift of minus T by 2. So now what I am gonna do? This was my D, this was my Q, this was my D, this was my Q. Okay, D naught, Q naught I can call, D1, Q1 I can call. So what I need to do? I need to go from here to here. The same thing I am doing. So first I will pass what would be my T clock. So T clock should be greater than or equals to TPD1 it was, right? TPD1 I am calling it. TPD1 plus setup of this minus T clock by 2. Minus of minus T clock by 2. Sorry for that. Minus of minus T clock by 2. The time required to reach here plus the setup margin minus this clock skew. This is what we were doing in the last lecture. Do you remember it? I hope you remember it. I am just showing it again. The total time required plus T setup minus clock skew of the clock where we are reaching. So clock skew of this where we are reaching. So what you get here? T clock TPD1 plus T setup 2 plus T clock by 2. So this will become T clock by 2 only. So T clock should be greater than 2 TPD1. What was your TPD1 here? 2 nanosecond. And what was your T setup? 5 nanosecond. 2 nanosecond plus 5 nanosecond. What answer you would get? That my T clock should be greater than or equals to 14 nanosecond. Okay, well and good. No doubt about that, right? If you had taken plus T by 2 here, what T clock by 2 here, what would be the issue? If you had taken plus T clock by 2 here, okay, this would be plus T clock by 2, then this minus would go here, this would become 3 T clock by 2. That is greater than this 5 plus 2, that is 7. So what you are getting? T clock by 2 should be greater than 14 by 3. So here eventually you are going to get lesser T clock value only. but we will pick the higher one. So to get the higher one, I need to take minus t clock by 2. So always remember, the phase shift I am always going to take, not phase shift, the delay I am going to take in negative only. If I take in positive, if I take this as positive, if I remove this negative sign, because phase shift is minus t by 2 as well, sorry, not phase shift, delay is minus t by 2 as well, and delay is plus t by 2 as well, both are same thing. But if I put plus t clock by 2 here, then the issue is becoming that my t clock should be greater than 14 by 3, and if I put minus t clock by 2, then it is becoming 14 nanosecond. So what answer I would expect? What answer I would take? I would take 14 nanosecond, right? So that's why I will always put negative delay. Okay, so this is not acceptable. So this I will just keep in a box and I will tell that won't consider. So I hope you must have understood the concept. Either you could have solved by these waveforms, timing diagram, you understood it. But then we analyze this very simple thing. What is that? That I can take this bubble out. If I take this bubble out, what do I get to know? That this is providing me a delay of minus t by 2. So this will work as a skew only. This is my clock skew. I can represent this as skew only. This will work as my clock skew. Solve the next question on your own. This question I am taking from DGQS, so all credit goes to this particular PDF, DGQS, whoever designed it. Okay, this question is not designed by me, this is designed by someone, DGQS, so all credit goes to them. So now this question is given, delay 2 mentioned, delay 1 mentioned here, clock to Q is mentioned, setup time is not required here because input is fixed, and setup time 2 is mentioned, and these 3 inverters are there. Both are positively triggered, 3 inverters are there. Okay, all combined give you delay of 3. So what should be your T clock minimum? So what you will do? What you will do? You will say that, sir, I will walk from here to here and I will see when my input is stable, because here input is already stable. I need to look at this input only. I can go from flop 1 to flop 2. So I will go from flop 1 to flop 2. So first I can start writing my T clock. That would be T clock should be greater than T dl by 2 plus TCQ1 plus T dl by 1 plus I have reached here, plus I need the setup margin of 2 minus what should be the delay here? What should be your T skew? What do you think? What should be your T skew? This will provide you a phase shift, no, not phase shift. This will provide you a delay of minus t by 2. This will provide you a delay of minus t by 2, and this will provide you a delay of minus t by 2. What is the total delay? Minus 3t by 2. What this can be equivalent to? Minus t by 2 only, no? Say yes or no? If you shift your clock by time period t, that means you are getting the same clock. This is my clock. This has a time period of t. If I shift this by t, I will get the same clock only, no? Or if I shift by minus t, I will get the same clock only. So what is left? Minus t by 2 left, na? Did you understand this point or not? This will give me a delay of minus t by 2. This will give me a delay of minus t by 2. This will give me a delay of minus t by 2. So total delay will be minus t by 2. I agree to this point. Total delay will be minus t by 2. Do you agree to this point? No, total delay will be minus 3t by 2. But in minus 3t by 2, there is minus t and minus t by 2. There is no meaning of minus t because minus t is making the waveform same. So this is equivalent to minus t by 2 only, right? There is no meaning of that. So it is equivalent to minus t by 2. So what I'm gonna write here? I'm gonna write minus t clock by 2 plus this delay as well. Look, these inverters are there. If here, what did I tell that? This is giving me minus t by 2, assuming that this bubble is having no delay of its own. If this bubble is having delay of its own as well, look, all these came considering that this bubble has no its own delay. Are you getting this point? All these analysis here, what did I do? I just simply wrote at the same time only. There was no introduced delay. I did not introduce any delay from my side. Now, I considered that this inverter is having 0 delay. This inverter is having 0 delay, right? Its own delay is 0. This minus t by 2 is coming from this analogy that we delivered here. Are you getting this point? So here this minus t by 2 is coming from the analogy, along with that it is having the delay of t delay by 3. So this total delay is t delay t dl by 3 t dl by 3 minus t clock by 2. The total delay, this is giving me a delay of minus t by 2, along with that it is giving me a delay of t dl by 3 as well. So that's the complete equation. So from here what you will get, that your t clock should be greater than twice of, because this will be plus, this will be minus, so this will go here, twice of t dl by 2 plus t cq1 plus t dl by 1 plus t setup 2 minus t dl by 3. Did you understand this particular question or not? A very good question, and very high chances that it can come in your gate examination, because every time they have asked the question when the clock was same. But what if we introduce a negative edge triggered clock, or we introduce inverters here? Instead of simple buffer, if we are introducing an inverters in the clock, then there can be an issue. What can be an issue? That clock is being inverted. And if clock is being inverted, this is giving me a phase shift of minus t by 2. This is also not phase shift, delay. Again and again I am calling it phase shift. This is giving me a delay of minus t by 2, minus t by 2 and minus t by 2. Overall delay minus t by 2, that is equivalent to minus t by 2 only. And it is having its own delay of dl by 3 as well. Own delay of dl by 3 as well. So total delay is t dl by 3 minus t by 2. So t dl by 3 minus t clock by 2. This is what I have written. So from here, this is the expression I get. So this is how I will be solving in the examination. I hope it is clear to you. I spent 20 minutes here. So just I wanted to tell that this was the clock. This was positive edge triggered. This was positive edge triggered. Again I am repeating it. I hope this point is clear. If it is not clear, then again I am repeating it. This is positively edge triggered and this is negatively edge triggered. But if I want to make it positively positively edge triggered only, then what I need to do? I just need to invert this waveform. I just need to add a buffer, add an inverter. If I invert this waveform, 0 will become 1, 1 will become 0, 0 will become 1, 1 will become 0. This is inverted, and then I can say at positive edge only I am getting the negative edge of this clock. So yeah, I can say now this is my positively edged trigger clock, but this we are getting by shifting it by minus t by 2. So by shifting it by minus t by 2 we are getting, so this is giving me a delay of minus t by 2. One more important thing I need to take care that if it is having its own delay, then that also I need to consider. So this is my final answer. Okay, so very high chances that these kind of questions I can expect in upcoming examination. Let's solve this question now. This question is also from DGQS only. You need to find the maximum frequency of operation for the following configuration. Okay, now there are 3 flip-flops connected. Till now we have studied only 2 flip-flops are connected, right? Two flip-flops are there. Now 3 flip-flops is connected. So what you are going to do? Let's just say I call this as flop 1, flop 2, flop 3. When I see a question based on STA, what will be the first thing I will be doing? I will be looking at the inputs. Stable input, no need to worry about that. Not stable, not stable. So that means I need to go to flop 2 and flop 3. That's my target, right? I told you one trick. You need to see the path. From where to where I can go? From flop 1 to flop 3 I can go. Flop 1 to flop 2 I can go. And flop 2 to, better I should write here. I can go from flop 1 to flop 2. Can I go from flop 1 to flop 3? You will say yes sir, you can go from flop 1 to flop 3. But in between there will be flop 2 only, no? Ram is there, Shyam is there, Mahesh is there. I need to go from Ram to Mahesh. Ram to Mahesh. In between Shyam will come. So better you say na, you go from Shyam to Mahesh only. Ram, Shyam, Mahesh. Ram can go to Shyam directly and Shyam can go to Mahesh directly. There is no direct connection between flope 1 and flope 3. Are you getting this point? A lot of people will be getting confused here. So I am going from flope 2 to flope 3, not from flope 1 to flope 3. Okay. So flope 2 to flope 3. I know one thing, a very simple trick. If I am going from flope 1 to flope 2, that means I will consider my input of flope 1 to be stable. So yeah, it is already stable. Okay. No need to worry about that. Or I will consider it to be stable. In this example, I considered it to be stable only. Where was that example? In the end, we wrote a conclusion. So there, here, even though it was not stable, still we said that we will consider it to be stable. Here also it was not stable. When I was going from flope 2 to flope 1, I still considered it to be stable. And when I was going from flope 1 to flope 2, I considered this input to be stable. So that we are going to do. Okay. Let's come back to our question now. So if I am going from flope 1 to flope 2, so what I will do? I will start working from here. I will go to CQ1, then DLY1, and then the setup time, right? So first I will set my input. So T clock should be greater than. There is no skew here. In this path there is no skew, right? In the path of this clock there is no skew, no? Skew is ahead. So T clock should be greater than or equals to T CQ1 plus T DLY1 plus T setup 2, setup margin, T setup 2. And when I reach here, I see the setup margin, and what else do I see? If the clock of this flip-flop is having some skew or not. Yes, the clock of this flip-flop is having some skew. So that skew I have to subtract. So that's it. This is my T clock for this. And what will be my T hold? Hold for 2 I will be writing, because if the data is stable here, I don't need to care about hold here. So hold for 2 I will be writing. I just need to erase setup time. Okay, then this is my hold, this is my clock. Now you are going from flope 2 to flope 3. Flope 2 to flope 3. So what you are going to do? You are going to consider this input as stable. Now from here to here you will work. So how you will work? Now if you are not getting satisfied with this explanation, then we are going to solve it with timing diagram as well, because I know a lot of people will not be satisfied with the explanation. But once we solve it with timing diagram, after that you will make a method. What is that method? No matter n number of flops can be there. Our target is just to work through the flops. That's it. So now I am working from here to here. A very interesting thing will come. You need to tell me. So what I am going to write? T clock. If I can call this as dash, then this will be double dash. So tell me now what I will write. T skew 1. First the skew will come, because if I am going in this path, skew is coming. So T skew 1 plus then clock to Q plus then this delay. Now my input is stable, so I will ask for setup time now. Now I need to subtract the skew of this flip-flop, right? What is the skew of this flip-flop? What is the skew of this? There is no skew of the flip-flop actually, there is a skew of clock. So this flip-flop is fed with this clock. And what is the skew of this clock? Skew 3, sorry, skew 2. No, this clock is having skew 1 plus skew 2. Because if you are starting from here, you will have skew 1 delay till this point. Skew 1 delay till this point. So if you are reaching here, that means you are having this much of delay, no? So this clock is having skew 1, T skew 1 plus T skew 2. Now T skew 1 and T skew 1 will be getting cancelled. So T clock dash will become T skew 1 and T skew 1 will be getting cancelled. So T skew 2 plus T DLY 2 plus T setup 3 minus T skew 2. So this is your T clock. So this was the interesting thing. We can move with the flops, but we need to take care how we will be moving. Again, I am repeating. From here to here I will go. I will see if there is any delay. No delay. T CQ2, T DLY. Then I will ask for the setup, and then I will subtract this skew. I was working from here to here. So there was a skew, then clock to Q, then this delay. Then I will ask for setup. Then I ask for setup, and then what I will do? I will subtract the skew of this clock. The flop where I am at flop 3 now. So I will subtract the skew of this flop, the clock of this flop. And what is the clock of this flop? That is this clock. And this clock is having total skew of skew 1 plus skew 2. Okay, so that was an interesting point here. So that's why we are getting this particular answer. Okay. And then TH3. So my TH3 will be, just the setup time will not come, rest all will be same. Now we will solve it by timing diagram, but do it on your own. If you are not satisfied with me, if you are not satisfied with my explanation, then you should do it on your own. Okay. But I hope you are satisfied with this approach. If you are not satisfied with this approach, then you should make the timing diagram and get to the final answer on your own. I will explain, but try doing it on your own. And if you are happy with that, then why should you do it? Okay. So again, I am repeating this approach. No matter n number of flip-flops can be there, you just need to work through the flip-flops. Flop 1 to flop 2 I can go, flop 2 to flop 3 I can go. I cannot come from flop 3 to flop 1. So that I am not writing. I am not coming from flop 3 to flop 1. I can go from flop 1 to flop 2, flop 2 to flop 3. I will see the delays, write down the setup, and then subtract the skew. See the delays, write down the setup, subtract the skew. That's it. Now, these two are the hold margin, which are different. Okay. Why did I put this greater than sign? Here it should be less than sign, right? Less than sign. So these are the setup margin which are different. What about the clock? The one which is maximum you will pick. So your T clock minimum will be maximum of T clock dash and T clock double dash, right? You will pick the maximum. That I have already told. The T clock should be greater than 13 nanosecond, T clock should be greater than 11 nanosecond. So you will pick 13 nanosecond. So that's it. Okay. Now let's solve it by timing diagrams. Will be a very tough job, but let's solve it because I am an educator. I need to solve it only. So let's start here. This input I am assuming to be 1. Okay. Input I am assuming to be 1. This is the clock. Now the clock is coming here. This is the clock. This is the original clock which is coming here. Now what will be the data at D1? Just as the clock comes, it will tell, I assume this as Q0, this as Q1, this as Q2. Just as the clock comes, it will tell Q0 to sample 1. It will tell Q0 to sample 1. But what Q0 will say? That sir, I will sample 1, but I need the delay of TCQ1. I need the time of TCQ1. So here I will receive the data after TCQ1 time. And if I am receiving the data here, that means I will receive the data after TCQ1 plus TDLY1 time. Okay, so I am directly writing the data at D1. So data at D1 will be TCQ1 plus TDLY1. Okay. Now, what is the clock at flop 2? Clock at flop 2. Now the job is to sample this data, right? The job is to sample this data now. So what is the clock at flop 2? What is that clock? That is original clock delayed by T skew. So original clock delayed by T skew. This is the clock at flop 2. And this is the input data. Input data at flop 2. Input data at flop 2. Now this clock will sample this data. So what this clock will say? What this edge will say? This edge will say that I know that my input is getting changed. So this much only hold margin should be there, right? So my TH2 should be less than what? How much is this margin? TCQ1 plus TDLY1 minus T skew1. There you go. So this is my TH2. Okay. What this clock will say? That I know that if I look ahead, my data is stable. But if I look back, I need this much of setup margin. If I look back, this much of setup margin I require. Okay. This much of setup margin I require. So T clock plus T skew1. This time window is T clock and this time window is T clock plus T skew1. Right? So what should be my T clock now? What should be my T clock? So T clock plus T skew1 should be greater than what? How much is this window? This window is TCQ1 plus TDLY1, TCQ1 plus TDLY1 plus TSU2, right? So what should be my T clock? My T clock should be greater than TCQ1 plus TDLY1 plus T setup 2 minus T skew1. Okay, this is my T clock. Were we getting the same answer here? Yes, we were getting the same answer here. Till now you are satisfied, but after that you will not be satisfied. That's the scene, right? So let's check. Now the thing will come on flop 3. So what is the input to flop 3? That is D2. So I need to write down D2 now. So how will I get D2? First I need to get Q1. I will get Q1 here, then I can get D2. So how will I get Q1? Q1 is the sampled data of D1. So this clock is sampling this data D1, this clock is sampling this data D1, and you are getting your D2 output, or you can say Q2 output. And Q2, after Q2 output, just delay it by DLY2 and you will get your D2 input. Okay. So what this will do? This will first sample 0, setup and hold time are meet. So first it will sample 0, okay, sample 0. Then it will sample 1 here, it is sampled 1. But now, here it was saying to sample 1. This clock was saying to sample 1. So it will sample 1, but what it will say? What my flop will say? That yes, I will sample 1. I am writing down D2 data now, okay? The clock, this flop will say that yes, I will sample 1, but I need a time window of TCQ2. And if I am writing at D2, then I need time window of TCQ2 plus TDL/2. So this much time is TCQ2 plus TDL/2. Are you getting this point? How I am writing D2? D2 is simply sampled data from this flop 2. Sampled data from this flop 2. So first I will get Q1. Q1 is the sampled data from flop 2. And which sampling? Sampling of D1. So now I am sampling D1. So here 0 will be sampled, 0 will be, initially it was 0, 0, 0, 0, 0. Now 1 will be sampled. So yeah, 1 will say that I will be sampled, but I need a time window of TCQ2 plus TDL/2 if I am coming at D2. Okay. Now tell me what will be this time? What will be this time? This time will be T clock plus TSQ1 plus TCQ2 plus TDL/2. T clock plus TSQ1 plus TCQ2 plus TDL/2. Say yes or no? Because till this time this was T clock plus TSQ1. This time would be just addition of that. So T clock plus TSQ1 plus TCQ2 plus TDL/2. Now this is the clock at flop 3. What is the clock at flop 3? Clock at flop 3. Skew1 plus Q2 added, just delayed. Skew1 plus Skew2. Okay. Now it will sample. Now what it will do? It will sample. Okay. Now its job is to sample. This clock will say that okay, for previously it is stable. Ahead also it is stable for a very long time. What this clock will say? Previously it is stable, but ahead I know it is changing its value. So this much of setup margin, this much of hold margin I need. So this will be my TH3. This will say that it will be stable at least till the hold margin. My input should not change at least till hold margin. So that is TH3. Better I should write somewhere here. So TH3, what is this margin? TH3 should be less than this minus this. This is your T skew plus T skew 2, and this is T clock plus T skew 1 plus T skew 2. Why I made this ahead of that? Why I made this ahead of this positive trigger? Because what is this? T clock plus T skew 1 plus T skew 2. And what is this? T clock plus T skew 1 plus T skew 2 plus T DL by 2. So certainly it will be large. Skew value are small only. In examination, you will be given the numerical data, so it will be more easy for you. Okay. But here I took this assumption, which is correct only, that this will come later on. D2 will come later on. After this clock it will come. Okay. So after this clock it will come. This is T clock plus T skew 1 plus T skew 2. So what is this margin? This margin minus this margin. Subtract this from this. Sorry. Subtract this from this. So T clock plus T skew 1 plus T CQ2 plus T DL by 2 minus T clock minus T skew 1 minus T skew 2. So this is getting cancelled, this is getting cancelled. So what you are getting? TH3, that you will be getting, and T clock is getting cancelled as well. So T CQ2 plus T DL by 2 minus T skew 2. Is that the same we got? Is that the same we got? Yes. So now you are building the trust on me. Say yes or no. Okay. So if I am saying something, I must have worked on it. Okay. You are not going to find this anywhere. These analysis, these timing diagram, it's not that easy. It is looking straightforward, but drawing this timing diagram in rough notebook and then having the guts to explain it. Okay. I think I deserve the appreciation here. I could have directly told this, but I know a lot of people will not be satisfied with this explanation. But since we have seen with timing diagrams, now you will be happy, right? Now anywhere you see the questions of setup time analysis, you will be able to solve it, right? It can be any flow can be there, any output, any input can be connected. You just need to know one thing. If input is not stable, I will work. I will assume one of the stable input and then I will keep on working. I will assume the stable input here, I will work. I will assume the stable input here, I will work. I will assume the stable input here, I will work. Here I don't need to work because this is the final stage. I can go from flop 1 to flop 2, flop 2 to flop 3. Flop 1 to flop 2 I will go, write down the delay and then subtract the skew. Here write down the delay, subtract the total skew. There you go. Otherwise, if I am not happy, I will do the timing diagram. Okay. So for T clock as well, you can write down the equation now, because what this clock will say? This clock will say that I need the setup margin. I need setup margin. So this clock will say, now I need my setup margin, that at least my input should be here. After that my input is stable, but before that input is changing, but it should not change at least till my setup margin. Okay. So now what you can write? This plus this is equals to this. T clock plus T skew plus TCQ2 plus TDL by 2 plus TSU3 is equals to 2T clock. Basically, it should be less than 2T clock plus T skew 1 plus T skew 2. So from there, what you are going to get? T clock should be greater than, basically this value should be greater than T clock and T clock 1 you will get, T skew and T skew will be getting cancelled, and here you are going to get TCQ2 plus TDL by 2. सेटअप कहाँ गया भाई? अच्छा ये रहा, प्लस TSU3 minus T skew 2. Okay, so this is what you will be getting. So now you are satisfied with the explanation as well. In the examination, you cannot do this kind of analysis. It will take a lot of time. So in the examination or even in the interview, you can tell them that, sir, I will work in the loop. I will assume the input is stable, because at some time input is going to be stable, and then I will go to the other loop. What if this output was connected here? What if this was connected here? Could you solve it? Yes, you can say that, sir, now I can work from flop 3 to flop 1 as well. So how I will be working? In this manner, and then this input is stable here, this input is stable, and then in that manner I will be going. Okay. Okay then. So I hope you must have understood this analysis, and this is from now onwards, gate aspirant can leave it. Okay, gate aspirant can uh, or gate aspirant can also watch one video that will be of around 1 hour only. So in the next video I am going to deal some interview questions. Okay, interview questions we are going to see. Someone is calling actually. Interview questions we are going to see in the next video onwards. So gate aspirant can also watch because you will be learning something new there. Okay, something new you will be learning. So, but placement guys certainly need to watch the next lecture as well. But if you are someone who is preparing for gate, this much should be more than enough for your examination. Okay, this much should be more than enough. You would be able to solve every single problem. Right? Okay then. So let's meet you in the next video. There we will be talking about some interview questions. So some interview questions we will see there. Okay. Thank you very much. Hi everyone. So continuing our discussion on STA. So now we are going to solve this question. Here in the first question you need to find maximum clock frequency, and in the second question they are saying that if you want to operate this circuit, if you want to operate this given circuit at a higher frequency than the calculated frequency, then what modifications you can do. Okay. So let's start one by one. Let's start with the first one. First let's find the maximum clock frequency. So that you can do very easily. So what I am going to write, T clock should be greater than what? I will work from here to here because this input is fixed. This input is fixed, should be fixed at 1 or anything. So I will work from here to here. So if I am working from here to here, what I will see? 6 nanoseconds plus 5 nanoseconds plus 3 nanoseconds and then setup time of this. 6 plus 5 plus 3. 6 nano plus 5 nano plus 3 nano plus setup time of this. That is 2 nano. Okay, working from here to here and then setup time of this. There is no clock skew, so we are not going to subtract any clock skew as well. Okay, so your T clock should be greater than what? Let's use calculator because I need to calculate the frequency as well. So it would be 16 nanosecond. So what would be your F clock? F clock should be less than 1 by 16 nano. So what I am getting? 16 reciprocal. So into 1000. So 62.5 megahertz. So F clock should be less than 62.5 megahertz. So this is my maximum frequency. Maximum frequency I can operate at 62.5 megahertz. Now in the second question what they are asking, and do I have the page there? No. I want to operate it over 62.5 megahertz. Over 62.5 megahertz. What I can do? What you can do? Introduce a clock skew. Right? If I introduce a clock skew, what will happen? That will be subtracted from here. Let's just say the clock skew is of 2 nanosecond. So now what will your T clock become? T clock should be greater than 14 nanosecond. That means your F clock should be less than 1 by 14 nano. And what is your 1 by 14? 1 by 14 is 71.42. So your F clock should be less than 71.42 megahertz. So maximum frequency has increased now. If I introduce a clock skew, or a clock delay, if I introduce that, so to calculate the T clock, what I am going to do? I will go from here to here, then I will subtract this clock skew. So that I am assuming if it is 2 nanosecond, then what will happen? My T clock should be greater than 14 nanosecond and my F clock should be less than or equals to 1 by 14 nanosecond. Right? So the maximum frequency will increase. So if I introduce a clock skew, that will increase my maximum frequency. Okay. So introduce a clock skew. Let it be, how much we should take? Let it be 2 nanosecond. So what will be your T clock? Basically in the path, this was the clock which was fed to flop 1. Now this will be the clock. Now this will be the clock which will be fed to the flop 2. There are combination circuit in between. They will remain as it is. Okay. So this skew I am introducing, that is of 2 nanosecond. So what would be my T clock? So this is your method 1. Okay. Method 1. This is the method 1 you can use. 6 nanosecond plus 5 nanosecond plus 3 nanosecond plus setup time minus 2 nanosecond. So your T clock should be greater than what? 14 nanosecond. So your F clock should be less than or equals to 1 by 14 nano. From here what you are getting, my F clock should be less than or equals to 71.42 megahertz. Okay, so this has increased. So F clock max, what is your F clock max? That is 71.42 megahertz. So here it was this. So this is your method 1. Okay, what will be the method 2? What else you can do? So method 2 is known as pipelining. What do you mean by pipelining? So I will introduce another flip-flop here. Then what will I have? I will have 3 flip-flops in cascade. So have we seen this kind of example? Yes, we have seen. Flop 1 to flop 2 you will go, and flop 2 to flop 3 you will go. Right? So what I am gonna do, in between the combination circuit, there are 2 combination circuit. In between the combination circuit, I am gonna insert one more flop. The same kind of flop I am inserting. Setup time of 2 nanosecond, clock to Q is 6 nanosecond. Setup time of 2 nanosecond, clock to Q is 6 nanosecond. The same kind of flop. All these flops are same, right? All these flops are same. So I am just introducing one more flop in between. Now what will happen? How will I calculate T clock? Go from here to here and go from here to here. This I am calling as flop 1. This I am calling as flop 2. And this I am calling as flop 3. So if I go from flop 1 to flop 2, flop 1 to flop 2, what should be my T clock? T clock should be greater than, here if I go, clock to Q is 6 nanosecond plus 5 nanosecond plus setup time of this. So here T clock should be greater than what? 13 nanosecond, right? And if I go from flop 2 to flop 3, so what I will write? How will I work? I will work from clock to here. So there is no skew. Directly I will come here. 6 nanosecond plus 3 nanosecond plus setup time of this, that is 2 nanosecond. So what is my T clock here? So T clock should be greater than 11 nano. So what will be the final answer? Your T clock should be greater than what? 13 nanosecond. Okay. So your F clock should be less than or equals to 1 by 13. What is 1 by 13? That is 76.92. 76.92 megahertz. So this is the maximum frequency which has been increased. What was our maximum frequency here? 62.5. By method 2, by introducing a flop in between, this is known as pipelining. So by introducing a flop in between, I have increased it. But what is the catch here? What is the catch? Latency will be increased, right? Let's just say I was collecting my final output here. So previously it has to go through this much of delay, right? Now it will have to go through this much of delay. So latency has been increased. Also the area is increased because you are introducing another flop. So area is also increased. Although you can run your circuit at higher frequency now, your circuit will be fast. You will be able to run it at a higher frequency, right? Here you are able to run it maximum at 62.5 megahertz. Here you are able to run it at higher frequency, but the latency has been increased. Also the area has been increased. So these are the drawbacks. Now what is the method 3? Very interesting method. Just look at it, just understand it. Okay. What do we see here? There are 2 combination circuit, right? The output of this is fed to the input of this combination circuit. Output of first combination circuit is fed to the input of this combination circuit. Now what could be the output of this particular combination circuit? It could be 1 or 0, right? Either 1 or 0. So now my combination circuit 2, it can have either 0, wait a second, it can have either 0 or 1. Now if input bit is 0, let's just say this combination circuit is inverter only. So if input bit was 0, it would give 1 output. If input bit is 1, it would give 0 output. So with respect to different bit, it would give different output, that I know, right? With respect to different bit, it would give 1 or 0 output. It may happen that for different bits, it is giving me same output as well. It could be anything. But worst case, we will take that with respect to different bits, it will give different output. What I can do? The issue is that here the delay are being added. That first you will wait for this 5 nanosecond, then you will wait for 3 nanosecond. So eventually this data will be stable after 8 nanosecond. 8 nanosecond plus this 6 nanosecond, right? This 6 nanosecond you cannot do anything. But something you can play with 5 and 3. What you can do? Think about it. What you can do? I will introduce a mux in between. Okay. Output of this output, I will feed as a select line. It could be 1 or 0 because this is a combination circuit, but it could give me output 1 or 0. Now at the input, what I will do? I will collect this combination circuit. I will connect this combination circuit. At one of the input, I will connect this with input 1 and I will connect this with input 0, because I know whether either I will get the input as 1 or as 0, because this one can give me 1 or 0. So I know that input could be either 1 or 0. Now just as the circuit starts, data will travel from here to here. Data will travel from here to here. How much time it will take? It will take the time 11 nanosecond. Here data will be reaching after 11 nanosecond, right? Just as the circuit start, this has a delay of 3 nanosecond, right? This also has a delay of 3 nanosecond. So now this 1 or 0 will be reaching after 11 nanosecond, right? Because this is connected here. So this 1 or 0 will be reaching after 11 nanosecond, but these data will be stable at 3 nanosecond itself. You are not able to visualize here. Let me make the final circuit and then you will be able to visualize. Okay. So now what I am gonna do is that this is the circuit I am gonna do. So basically the output of first combination circuit I am connecting as a select line, 0 and 1, 3 nanosecond and 3 nanosecond. So just as the circuit starts, what will happen? This data will travel. It will reach here at 11 nanosecond. It will reach here at 11 nanosecond. Say yes or no? But what will happen is that these data would have been already stable, because with respect to one input, whatever the output is give, I don't know whether it will give output 1 or whether it will give output 0. I don't know that, but this will be stable at 3 nanoseconds. Say yes or no? And this will also be stable at 3 nanoseconds. So when it is coming at 11 nanoseconds, these are already stable. So this 3 nanosecond time they will not take. Now based on, let's just say if bit 1 is coming. So if bit 1 is coming, then this should be going out, right? I1 should be going out. So now how much time I1 will take to go out? Only the delay of this, which I will try to keep as low as possible. I am trying to keep the delay of mux as low as possible. Let's just say the delay is 1 nanosecond only. So this output will reach here after what? 11 nanosecond. This is already stable. So 1 nanosecond time or more it will take. So this input will be stable at 12 nanosecond. Previously it was being stable at 6 plus 5 plus 3. 6 plus 5 plus 3. Right? So that was 12 nanosecond, right? 6 plus 5 plus 3. Sorry, 14 nanosecond. So this was 14 nanosecond. So it was being stable at 14 nanosecond. But what we have done is that, this input will be stable at 11 nanosecond, which is the select line, and these are already stable now, because we know that this can either give me 1 output or 0 output. So 1 output or 0 output will be fed as an input to the combination circuit 2, and that I am already giving it. I am giving 1 or 0. Okay. So with respect to 1, whatever the output I will get, with respect to 0, whatever the output I will get. So here I will apply either 1 or 0. If 0 is applied, then this 0 will be here and this will be fed, right? If 0 is applied, what do you expect? You should expect that combination circuit 2 to give the output as per the input 0. If 0 is applied, what you would expect? You would expect the combinational circuit 2 to give the output as per the applied input 0. Do you agree to this statement? Right? As per the applied input 0. So if 0 is applied, then it will take this output. Which output? This output. Because I have already applied 0. From my side only, I will apply 1 as well, 0 as well. From my side, 1 as well and 0 as well. And then I will receive the output after 3 nanoseconds itself. Now 0 or 1 will come, so it will pick this or pick this. So these are already stable. when this input came, these outputs are already stable, so it will take 1 nanosecond of time more. So now my input is reaching here after 12 nanosecond. So what will be my T clock requirement? So let's move it off. These are already stable. This is coming at 11. So what will be my T clock requirement now? So T clock requirement, if I write from the beginning, so 6 plus 5 plus these are already stable, so it will take just 1 nanosecond of time more, and then setup time, which is 2. So now my T clock requirement is, what is that? T clock requirement is 14 nanosecond. Okay, so from F clock what I am getting? 71.42. So again I have increased the clock frequency here, that now my circuit will allow 71.42 megahertz clock frequency. Okay, and here there is no issue of latency. Why there is no issue of latency? Because you are not increasing the circuit. Here what was the scene? You are basically you are going from here, then it will have to go through the clock to queue of this one as well, and then clock to queue of this one as well, right? But here what will happen? You did not introduce any other flip flop. What you just did, you went from here to here, then take the output and again. So latency is not increased here. Latency is decreased only, because previously it was taking this time and the time of this combination circuit, and then it was reaching here. But now what it will take? This time, then this time, and time of this, which is 1 nanosecond. So if your mux was having more than 3 nanosecond of delay, let's just say if mux was having 4 nanosecond delay, then this method was not useful for you. Why it was not useful? Because mux would take 4 nanosecond of time to give the output. So this time would have become, what it would have become? 15 nanosecond. Then 15 plus 2, it would be 17. So that is of no use. If mux is having lesser delay than this combinational delay, so that is useful for you. So these kind of interesting interview question can be asked, and even the numerical problem can also be framed, right? So that's why it is important for GATE aspirant as well, and certainly for interview guys as well, for placement guys as well, right? So how it will be coming and how it will be transferred. So important for both. So they can ask you like what methods you can use. So first you can say that I will introduce a clock skew. Then I can introduce a pipelining as well. I can do the pipelining as well. Okay, generally we do not introduce any clock skew from our own side. When you go to the industry, you will not see that you are introducing clock skew from your own side, because this buffer you will have to make. Now this buffer will load this clock, right? So at the clock you do not want much load, because this clock is already loading this flope, right? This flope it is already loading. Now you want this clock to load this particular buffer, and then this buffer will load this particular flope. So that much loading you do not require. So this is not an ideal method. You will never use, from your own side you will never introduce any clock skew. Okay, so this is not a good method. But this method we can use pipelining, but here data latency will be increased. But if we are having a mux which have a lesser delay, then we know that here we are having 1 or 0. So if we are having 1 or 0, then I could directly get my output of 1 or 0. Already stable output is there in 3 nanosecond itself. When this data is coming, my inputs are already stable here, so it will just take a delay of 1 nanosecond. So after that it can give me output. Okay, so that's the best possible method, right? So this was one of the question. Let's move to the next one now. So this question is given. First question is not based on STA. What is the output frequency? What is the output frequency? Here you can see that my flow, like this you can assume as a buffer only. Okay, I will write here, this is a buffer, because Q bar is directly fed here. So what will be your Q plus? Q plus will be equals to D, and D is equals to Q bar. That means in which mode it is? Toggle mode. Toggle mode. That means it is working as a asynchronous counter. So what will be your F out? That would be F in by 2. So it had nothing to do with our STA, right? Let's see the second one. What is the minimum time period, okay, of the clock? So what that would be? Here only there is one flop. Okay, there is only one flop, and the input of this flop is not stable. You can come from flop 1 to flop 1 only, right? The input of this is coming from the output of flop 1 only. So where I can work here in this particular configuration, where I can work? Flop 1 to flop 1 only. Say yes or no. I can work from flop 1 to flop 1. So where I will work? Let's write it here. Flop 1 to flop 1 only. Okay. If I'm working from flop 1, so I'm assuming this data is constant. So how I will work? I will work in this manner, right? So let's work now. So first this skew will come, T skew, plus then clock to Q will come, that is 1.5 nano. Then what will come? Then this delay will come. From here to here you are going, then this delay 0.2 nanosecond is also coming, plus 0.2 nanosecond, right? And then you have reached here. If you have reached here, then you need to take setup time in action. Also, you need to subtract the skew of this flop, skew of this flop, skew of the clock of this flop. And what is the clock of this flop? This is the clock of this flop. And what is the skew of this? That is T skew only. So this T skew and T skew is getting cancelled. So your T clock should be greater than what? What I did, I worked from here to here, then clock to Q, and then I saw this delay, then plus 0.2 nanosecond, then I reached here. If I reach here, I see I require a setup time of 1 nanosecond. So that I wrote. That's it. So what do I get? 2.7 nanosecond. So this is my requirement. Okay. Now, is there any hold violation? Is there any hold violation? So what is your hold requirement? Hold requirement will be same as that, just this setup time will not come. So your hold should be less than T skew, and T skew here also will be getting cancelled. Only this setup time will not come. So it should be less than 1.7 nanosecond. Your T hold should be less than 1.7 nanosecond. But what do you see? But why I am writing TH2? Only one flop is there now. So TH should be less than 1.7 nanosecond. But TH is equals to 2 nanosecond. That is given. So yes, there is hold violation. Do I have the page? No. Yes, there is hold violation. Now fourth question, they are asking any effect of slew. No, slew is getting cancelled. No, skew, sorry, not slew. Any effect of skew. No, skew is getting cancelled. So no effect of skew. In one flop only, if you are working in this loop only, so there is no effect of skew because skew is getting cancelled. First it is delayed and then you are cancelling it. Then you are subtracting it. So skew is getting cancelled. So no effect of skew. Any suggestion to avoid hold violation? Which suggestion you will do? You will tell. You need to increase this time. What was this time? How did you get 1.7 nanosecond? How did you get 1.7 nanosecond? That was 1.5 nanosecond plus 0.2 nanosecond. So clock to Q you cannot do anything. Clock to Q you cannot do anything because this, when you have designed this flop, then it is fixed. Clock to Q is fixed. But this is your external delay. So what you can do, you can introduce another buffer or you can just increase the delay of this buffer. So what you can do, increase DLY delay. Because if I increase it, let's just say if I make it 1 nanosecond, then what will happen? TH would be what? 1.5 nanosecond plus 1 nanosecond. But this clock requirement will also change. Okay, you need to take care that this clock requirement will also change. If you increase this delay, then your hold margin can be improved, but this clock requirement, T clock requirement will also change. That will also increase. So if I make this as 1 nanosecond, from 0.22 if I make this 1 nanosecond, then what will be my hold requirement? That would be less than 2.5 nanosecond. And what is the given hold time? That is 2 nanosecond. So now we are happy. Okay, so what suggestion you will do? The suggestion you are giving is that increase the buffer delay. Okay, increase the buffer delay or DLY delay. So if I increase it, my hold requirement will increase. Sorry, hold requirement will decrease, you can say, or basically you will have more margin, right? So this you can do. So fifth answer I am writing here only. If DLY goes to 0.5, okay, 0.5 only, then what will happen? That your T hold should be less than or equals to what? 1.5 nanosecond plus 0.5 nanosecond. So your T hold should be less than or equals to 2 nanosecond. So yes, this is acceptable. This is acceptable, right? Let's see the next question. So looks like a very simple question, but a lot of data are given. Here T minimum, T max is written. Okay, this is 2 nanosecond. T minimum, T max is written. So there is very rare chance that this kind of questions they can ask, but what if they ask? So what do you mean by this minimum maximum? Look, this wire is also having a delay. This inverter is also having a delay. This is also having a delay. This wire is also having a delay. This buffer is also having a delay. This wire again is having some delay. This is certainly having some clock to Q delay. Minimum and maximum. Hold and setup time are there. And this is the T clock. Applied T clock is 15 nanosecond. So T clock is also there. Now they are saying if there is any setup or hold violation and find the setup slack. What is setup slack? That I will tell. What is setup slack? What is hold slack? So that I will tell. But if I just need to write down that T clock, if I need to write down T clock minimum, basically, what do we solve? How do we solve? I just write down that my T clock should be greater than this thing. So what we do? This input is fixed. We are working from here to here. So now I will work. Just as I work, first delay I see this. So here there are two delay mentioned, 1 nanosecond and 2 nanosecond. Okay. Now I need to write either 1 nanosecond or 2 nanosecond. Look, if I work from here to here, the first delay I see is that 1 nanosecond and 2 nanosecond. So tell me whether I will write down the maximum delay or minimum delay. What do you think? You want this T clock to be greater than some value, right? If this T clock is greater than the maximum value, then I am happy, or if it is greater than some certain value. Let's just say what I mean to say is that if my T clock is greater than 5 nanosecond, one condition I am getting this, and another condition I am getting is this. The T clock should be greater than 8 nanosecond. Okay. So which condition you will be happy? In this one, no. That if my T clock is greater than 8 nanosecond, then certainly 5 nanosecond is already fulfilled. If my T clock is 9 nanosecond, then 8 nanosecond is also fulfilled, or this is also fulfilled. But if my T clock is 6 nanosecond, then this is fulfilled, but this is not fulfilled. So here what you are going to write? You need this value to be maximum. Say yes or no. So if my T clock is greater than the maximum delay, then it is good for me, no? Right? So here I will write down the maximum delays. So first 2 nanosecond, then clock to Q also I will write maximum. So 2 nanosecond plus 11 nanosecond plus, then this wire is having delay, that is 2 nanosecond. Maximum delay I am writing. Then buffer is having delay. Maximum delay only I will write 9 nanosecond and then 2 nanosecond. 9 nanosecond and then again 2 nanosecond. 9 nanosecond, again 2 nanosecond. And after that, I will see the setup requirement, that is 4 nanosecond. It cannot be maximum or minimum because this is a fixed value. Okay. So this is my all the maximum I am taking. All maximum. Okay. Let's check back again. 2, 11, 2, 9, 2. 2, 11, 2, 9, 2 plus hold. Minus. You need to subtract clock skew. What all are the clock skew here? These are the clock skew. Will you subtract maximum or minimum? What do you think? Will you subtract maximum or minimum? I will subtract minimum so that this value becomes maximum. This is my target, that this value becomes maximum. This complete value should become maximum. Say yes or no. This complete value should become maximum. So I will subtract minimum here, no? So I will subtract the minimum clock skew, that is 2 plus 5 plus 2. 2 nano plus 5 nano plus 2 nano. Overall value I want maximum. So from maximum I will subtract minimum so that I get maximum. Okay. So T clock should be greater than what? Let's add it up. 20, 24, 26, 30. 30 minus 21. Let me check it again. 15, 17, 20, 17 or no, 26, 30. 13 nanosecond minus 9, 21 nanosecond. So T clock should be greater than 21 nanosecond. But T clock is equals to 15 nanosecond. This is given. So certainly there is some issue in the setup time, right? There is some issue in the setup time. This is your setup time, right? This was your setup time, which was 4 nanosecond. If it decreases, if 4 nanosecond decreases, then this value will decrease. So there is setup violation. Setup violation. Look, T clock has nothing to do with the hold violation. T clock has nothing to do with hold violation. So certainly there is a setup violation. Now tell me by how much margin your setup time should be decreased. You are saying that my T clock minimum I require is 21 nanosecond. You are not going to change this wire delay, nothing will change. Only change you are going to do is the setup time change. Okay, you need to change the setup time. So by how much margin your setup time should be decreased? 21 nanosecond and 15 nanosecond. By how much margin your setup time should be decreased? By 6 nanosecond, right? If I subtract 6 nanosecond here, if I subtract 6 nanosecond, if my setup time was minus 2 nanosecond, if my setup time was minus 2 nanosecond, then there was no issue. I would have gotten T clock should be greater than 15 nanosecond only. Or here only you can see this is becoming 21 and this is 15 required. So 6 you need to subtract. 6 you need to subtract. So this is known as setup slack. Okay, this is known as setup slack. So I will write setup margin, setup time should be decreased by 6 nanosecond. So what is your setup slack? Setup slack is equals to minus 6 nanosecond. It should be decreased, right? So it is negative. Okay, so minus 6 nanosecond. So this much margin you need to decrease. So setup slack is minus 6 nanosecond. So this was the first part. Let's check if there is any hold violation. So what will be my hold time? So my TH2 should be less than what? Everything will come, but this 4 nanosecond will not come. So my TH2 should be less than, no, wait. Now, your TH2 should be less than a particular value. Your TH2 should be less than a particular value. So what you will take here? Minimum or maximum? TH2 should be less than 2 nanosecond and TH2 should be less than 4 nanosecond. If I take TH2 equals to 3 nanosecond, this guy is happy, but this guy is not happy. If I take TH2 equals to 1 nanosecond, then this guy is also happy and this guy is also happy. So what I need to take? I should be, if I am going towards minimum, then I should be minimum from the minimum possible value. I should be less than the minimum possible value. So I will take the minimum possible values here. So now what I am going to take? I am going to take the minimum possible values, right? Because I want it to be less than the minimum. So what is the minimum I am going to take? 1 nanosecond plus 9 nanosecond. So first all the delays I will take. 1 nanosecond plus 9 nanosecond. 1 nanosecond plus 9 nanosecond plus 1 nanosecond plus 1 nanosecond plus 6 nanosecond plus again 1 nanosecond. Now I have reached here. I do not require any setup margin. I will just subtract the skew. So what I am gonna subtract? Maximum or minimum? Maximum, because I want this complete value to be minimum. So I will subtract maximum now. So 3 plus 9 plus 3. 3 nanosecond plus 9 nanosecond plus 3 nanosecond. Do you need to mug it up? No. You will think on your own. Okay, I need T clock to be greater than some value. That means I want it to be maximum. So I will take maximum here and in the subtraction I will take minimum. I want my T hold to be less than a particular value. That means first I will take minimum only and in the subtraction I will take maximum. So here I started 1 minimum I am taking 1 plus 9 plus 1 plus 6 plus 1. No need to mug it up. Minus maximum I will take. 1 plus 9 plus 1 plus 6 plus 1. Then maximum I am going to take 3. Skew I am subtracting, right? 3 plus 9 plus 3. Okay. So your TH2 should be less than what? 10, 12, 18. 18 minus 15, 3 nanosecond. Okay, let me check back the calculation again. 10, 18, 18 minus 3, 15, 15 minus 12, 3 nanosecond. So TH2 should be less than 3 nanosecond. And what is given? TH2 is 4 nanosecond, 2 nanosecond. Yes, TH2 is equals to 2 nanosecond. This is given. This is given. So certainly, I was asking it to be less than 3 nanosecond. It is certainly less than 3 nanosecond only. 2 nanosecond is less than 3 nanosecond only. So there is no hold violation. Okay, so that's it. This is how we need to solve this problem. A very easy problem it was. Just there was too much of data. So how to handle these data, maximum and minimum? Like here the delays are the maximum and minimum. So what do you understand by that? One is contamination delay, one is the propagation delay. I told you contamination delay and then propagation delay. So one is contamination delay, another one is propagation delay. Okay. So in that manner we are going to solve. So this I wanted to be minimum only. So here I can write minimum. Now in the interviews these kind of questions can be asked. They can ask you, what do you mean by the setup time and hold time of a latch? Till now in complete lecture we were studying only the flip-flops. But what do you understand by setup time and hold time of a latch? So it is very interesting. What would you think? If you don't know this concept, then what would you think? What should be the setup time of a latch? You know the working of latch, right? This is a positive level latch. What it will do? At positive level, it will detect the data. After that, at negative level, it will hold. Then again at positive level, it will detect the data, then it will hold. So I will just write down sample. Here it will sample and then it will hold here. Here it will again sample. After that, it will hold. Sample the data and then hold it. Sample the data and then hold it. Right? So if you think at the first glance, what you would say that, sir, just as this positive level is coming, just as the positive level is coming, they should be set up here and there should be hold here. But this is not the correct definition. Okay. The definition is when your sample operation is about to end, at that time it will look back and it will look ahead. So this is known as latching edge. Latching edge. So when the positive level, when the sampling is about to end, there it will see, at this latching edge it will see that yes sir, I will sample the data correctly, but my data should be stable for the given setup time. This is the setup requirement and this is the hold requirement. So my data should be stable for the previous 3 nanosecond. My data should be stable for the previous 3 nanosecond. So here at the latching edge it will see that if my data is stable for previous 3 nanosecond or not. Previous 3 nanosecond, that means 12 to 12 minus 3. What that would be? 9 nanosecond. So from 9 to 12 nanosecond it should be stable. Yes, it is stable. Okay. What else it will see? That even after the latching edge, that means my sample operation is done. Even after that it should be stable for next 2 nanosecond. It should be stable for next 2 nanosecond. So what is 12 plus 2? That is 14 nanosecond. So from 9 to 14 nanosecond it should be stable. So yes, it is stable. From 9 to 14 it should be stable. That means there is no setup or hold violation. So first definition is, what do you mean by latching edge? So latching edge is when the sample operation is about to end. That is known as latching edge. This is not the latching edge. This is the latching edge. When my latching is about to end. So at the latching edge it will see whether it is stable before and after. So this was your setup time requirement and this was your hold time requirement. Okay. So this is what it will see. Understood this point? Okay. Let's see it in negative edge triggered. So in negative edge, not negative edge, I should say negative level triggered. So here it will hold. Here it will sample. Here again it will sample. This is negative level triggered. Here it will hold. The same example is there. Ditto same example is there. So here it will sample. So now where the sample is about to end? At this edge. So this is known as latching edge. This is your latching edge. Now at this latching edge, what it will see? Before and after. Before and after. So before 3 nanosecond setup time. Setup time means it will look before. So it should be stable for 3 nanosecond here. And after 2 nanosecond it should be stable. So this time window is 20. So 20 plus 2, 22 nanosecond. So yes, it is stable because this is 24 and 20 minus 3 17 nanosecond. Yes, it is stable because this is 16 nanosecond. So from 17 nanosecond to 22 nanosecond your input should be stable. Then there will be perfect latching. Sample operation or hold operation, the operation will be perfect only if it is stable in this time window from 17 to 22. So this was asked to me in my TI interview. Okay, so this was asked to me as well, that what do you mean by setup time and hold time of a latch, because generally we study about flip flops only, but we should know what do you mean by setup time and hold time of a latch as well. So it seems like that it will be looking at the starting, but it's not the case that it will be looking at the starting, it will be looking at the ending. Okay, so I hope you must have understood. This is the definition. What is the setup time of latch? The minimum time input needs to be stable prior to the latching age. Okay, prior to the latching age. And what is the hold time of a latch? Minimum time input needs to be stable after the latching age. Okay, after the latching age, right? So here is also there is no setup or hold violation. There will be no numerical question from this particular topic, just a simple fact they can ask. Okay, sometimes like if they want to test your deeper knowledge, they can ask these kind of things, that what do you mean by setup time and hold time of a latch. So just this definition you need to tell, or you can simply draw the diagram and you will tell that sir it will look back and look ahead, it should be stable for the given time. Solve this and this question on your own. How to fix setup violation and how to fix hold violation. These two will be our last question. Okay, options are mentioned. Think on your own. I will pause the video. Write down your. This is a MSQ question. Okay, MSQ means multiple select question. More than one option is correct. I will pause the video, drink some water, and then we will see the solution of it. So solve it on your own. Okay. Yeah. So let's start solving this problem. How to fix setup violation. So setup violation is associated with clock. You remember it? Do you remember this equation? T clock should be greater than all the delays. Let's take any example. All the delays plus setup time. All these delays plus setup time. Right? All the delay. So this I am denoting as TD. So all the delay I am calling as data delay, because data will be stable after TD delay. So this is known as data delay plus T setup, right? So from here what you can see is that my T setup is less than T clock minus T D. Now what is the first option is saying? Speed up the clock. If you speed up the clock, what does that mean? You are decreasing that T clock value. This is my speed. Speeding up means increasing the frequency. Speeding up means increasing the frequency. What does this means? That if you are increasing the frequency, and increasing the frequency means you are decreasing the time period. Okay. So let's just say initially this value was 5 nanosecond. 5 nanosecond. Okay. Initially this value was 5 nanosecond. So what your circuit was saying, that you need 5 nanosecond of setup time. That your setup time should be less than 5 nanosecond. So you designed a flow where your setup time was 5 nanosecond only. So you are meeting this requirement. Now if you are speeding up the clock, that means you are decreasing this T clock. So what will happen? This value will decrease. So now what your flow will say? Your flow will say that your setup time requirement is 4 nanosecond now. That maximum you can take 4 nanosecond. And you designed this flip flop now. You designed this flop, which is having a setup time of 5 nanosecond. Now this is saying that your maximum setup time can be 4 nanosecond. Maximum can be 4 nanosecond, but you are having 5 nanosecond. So will that be happy? No. So this is not a correct option. If you think too much, you will not be able to understand it. Okay. Just understand by this analogy that this is my equation. Simple, this is my equation. Okay. Now, initially this value was 5 nanosecond. I am assuming any initial value. This was 5 nanosecond. T clock minus TD. So I designed my flip flop with 5 nanosecond of setup time. But when I speed up the clock, what will happen? This T clock will go down. If this T clock is going down, then this value is going down. So now what my flop is saying, that your setup time maximum can be 4 nanosecond, but you designed it for 5 nanosecond. You are increasing the problem or you are decreasing the problem? You increased the problem, no? Your problem got increased. First 5 nanosecond was good enough for you, but now they are saying that maximum you can apply 4 nanosecond. So that is not acceptable. So this is not a correct option. Second one, speed up the data. Okay. So again, I am assuming this as my initial value only, that initially my TD was, so initially this T clock minus TD was 5 nanosecond. If I speed up the data, what does that mean? That I am decreasing the data delay. Speeding up the data, that means decreasing data delay, right? Data is reaching faster, that means delay is less. If delay is less, then what will be your setup time? If this value is getting less, then this value is getting increased, so it will increase to 6 nanosecond. So initially you designed a flow with 5 nanosecond of setup time. Now they are saying that your setup time should be less than 6 nanosecond. So are you happy? Still are you happy? Like initially you designed it with 5 nanosecond. Now even if your setup time is 5.5 nanosecond, still this guy is happy, because this guy is saying that your setup time should be less than 6 nanosecond now, right? So still you are happy now. So if you decrease the data delay, or if you speed the data, if you speed up the data, or you can say if you decrease the data delay, then this value is getting increased. That means now your setup time requirement has increased. Now I should not say setup time requirement has increased. Now you can say that setup time, no, I should not, which word I should use? Setup time, that setup time window has increased. I would say setup time window has increased. Okay, now your window has increased, that you can afford having 5.5 nanosecond of time as well. So yes, this is correct. Okay, so in that manner you need to think. Increase data delay. If you increase this, then what will happen? If you increase this data delay, what will happen? This value will go less, and if this value is going less, then what it is saying, that your setup time should be maximum 4 nanosecond, but you have designed it for 5 nanosecond. If you increase the clock period, if you increase this clock period, then what will happen? If you increase this clock period, then this value will increase. And if this value increase, what it is saying, that the maximum setup time you can have 6 nanosecond, you have designed for 5 nanosecond, you are happy. So B and D are correct. Okay, so in that manner you will think. So this is how you are going to think in the examination. Okay, so I will just write down T setup 4 nanosecond. So this we are getting in option A and C, and this we are getting in option B and D. So when you revise, you will be able to understand what we wrote. Okay, let's see the next one. You should be able to answer it on your own. So what was your hold requirement? T hold should be less than what? Data delay minus skew. Look, here also I could have introduced skew. Minus T skew, but no option was framed in terms of skew, so I just ignored it. Okay, there also I could have done the same thing, minus T skew I would have introduced and pick it here. In case of T hold, what will happen? First you will see the data delay, and then no use of setup time, just decrease the skew. So T hold doesn't even depend on clock, so this option is already gone. Speed up the clock, there is no meaning of that. T hold doesn't even depend on the clock, right? Speed up the data. So let's just say initially this was some 5 nanosecond, and for 5 nanosecond I designed it. Now it is saying speed up the data, that means decreasing TD, right? Decreasing TD. Speed up the data means decreasing data delay. So if that is decreased, if this is decreased, then what will happen? This value will go down. Now it is saying that maximum hold time you can have is 4 nanosecond, but you designed it for 5 nanosecond. Are you happy? No. Are you getting this point? Increase the data delay. If you increase it, then this value will go up. So now it is saying that maximum you can have 6 nanosecond, but you designed it for 5 nanosecond. Yes, you are happy. Reduce the clock skew. If I reduce this clock skew, what will happen? If I reduce this clock skew, this value will go up. So this will become 6 nanosecond. If I reduce this T skew, so this complete value will go up. So that means this will become 6 nanosecond. Again you are happy, because if this is becoming 6 nanosecond, it is saying that maximum you can have 6 nanosecond, but you designed it for 5 nanosecond. So yes, you are happy. So this is also correct. So in that manner you need to analyze. Okay, so here also I will write that this you are going to get in C and D option, and this you are going to get in A and B option. So these are the ways. So they can directly ask in the interview, what are the ways of fixing hold violation? Either they will ask with the circuit, here we solve these kind of problems with the circuits, or they will ask with the direct options as well. Okay. So from my side, that's it about STA. STA is a very vast topic. We can keep on studying this particular topic, but we cannot spend so much of time on that. We have to cover other things as well. So in a general interview, whether it is a back-end interview or front-end interview, I guess this should be enough for you. In a general interview, you can solve more problems. There are a lot of problems. There are a lot of videos on STA. You can keep on studying those videos. One thing I can guarantee, from after watching this video, if you watch any other video on STA, you will understand every single thing there. Every single thing you will be understanding. It will not be you will not be feeling like that I am not able to understand this particular video. From now onwards, after watching this video. So from my side, that is more than enough as per me. But it depends on the interviewer how much depth he requires. In a general interview, I would say in 80% of the interviews you will be able to survive with this much of knowledge. But if some interviewer is too much focused on ST only, he is not asking about FSM, he is not asking about counters. We have covered all these things, right? In a very in-depth manner, we have covered counters as well, we have covered FSM as well, combination circuit we have covered, flip-flop, latches, all these kind of things. We are going to cover CMOS VLSI as well. So all n number of topics are there which we are covering in a very good manner in digital electronics. So if he is focusing on those topics as well and on STA as well, then it is fine. But he is only focusing on STA. If your complete interview is going on STA only, then it might be difficult because he can ask anything, right? A lot of terms he can introduce, like he can keep on asking internal structures, but not 80%. I would say 90% of the interviews. In 90% of the interviews, this would be more than enough for you. Okay, this would be much more than enough, right? So that's it from my side. I hope you enjoyed this video. If you enjoyed it, try sharing it with your friends. Let them know that this kind of concept has been taught here. Okay then, thank you very much.